The Big Bang wasn't the beginning of everything. It may have been the beginning of time itself. And in our best equations, the moment before it isn't blank, it's crowded with something we can't see. So what did the universe explode out of? Another cosmos, a quantum field, a timeless structure, or a trap in the way human minds imagined before? Every origin story has a missing frame. In cosmology, that missing frame is where our most trusted laws begin to argue with each other. Look closely at the sky, and you're not seeing space. You're reading evidence preserved in light. The galaxies retreat, the microwave afterglow, and the faint chemistry of the first minutes form a case file that points back to an early blistering state. Yet when we push that reconstruction to its limit, the trail does not end with an answer. It ends with a breakdown. General relativity carries us toward a boundary where densities soar, and familiar geometry loses its meaning. Quantum theory, meanwhile, insists that even the calmest vacuum is structured, restless, and mathematically alive. Put them together, and the simplest question becomes the most dangerous. Not merely how the universe evolved, but what it means for anything to begin. Because a beginning is not just an event, it is a claim about time, causation, and the rules allowed to exist. If time is part of the system, then asking what precedes its first tick may be like demanding a longitude beyond the pole. Grammatically correct, physically incoherent, and still, our equations keep leaving fingerprints near that boundary, patterns that look less like emptiness and more like a hidden architecture. This is where the story turns unsettling. The closer we get to the earliest moments we can describe, the more nothing behaves like a medium with properties, constraints, and measurable consequences. Empty space can press on metal plates, horizons can radiate, acceleration can mimic heat, and tiny fluctuations can be stretched into the seeds of galaxies. These are not poetic metaphors. They are laboratory-grade clues that the void may be the most active ingredient in the cosmos. But clues are not conclusions. Cosmology is a forensic science conducted across billions of years, and every inference must survive the harshest courtroom: observation. Some ideas promise a brief explosive growth that smooths the universe and prints a subtle pattern into the afterglow. Others imagine a universe that passes through a contraction, a bounce, or a cycle, turning what looks like a first moment into a transition. And some proposals go further still, suggesting that what we call time could be emergent, a byproduct of deeper relationships that do not flow at all. If that possibility is true, then the most disturbing discovery is not a hidden place where everything started. It is the suggestion that reality can be consistent without providing the kind of before our minds demand, while still leaving behind rules, boundary conditions, and traces we might actually test. Across this documentary, we will follow the evidence from the expanding universe back toward its sharpest edge, then press against that edge until it gives. We will enter the physics of the vacuum, where zero is not simple. We will examine the mechanisms that could have amplified the smallest quantum irregularities into the cosmic web. We will weigh scenarios that replace a beginning with a bridge, and we will confront the possibility that the deepest layer of the world is not made of things at all, but of constraints, relationships written into mathematics. And then we will ask the final question, the one that remains after every model is built and every dataset is consulted. If the universe did not come from nothing in the ordinary sense, why do these laws exist, rather than any others, or none at all? Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. We begin at the cosmic crime scene, then descend into the strange physics of zero, and the early expansion that shaped everything we see. From there, we test bounces, multiverses, and emergent time against the only judge that matters, the afterglow still written across the sky. The Big Bang is often told as a moment of creation, a flash that made everything at once. In science, it is something narrower and more powerful, a model of an early hot, dense state and the expansion that followed. It is not an explosion into an empty room. It is the changing of the room itself, where distances grow because space-time's geometry evolves. Cosmology treats the universe like a crime scene with surviving evidence, scattered across the sky in faint signals. We cannot rewind a film, but we can read traces in light and matter, then cross-check them like forensic analysts. Those traces point back to a time when the cosmos was smaller, hotter, and smoother. They also point to a limit where our words begin to fail and where equations start to argue with one another. Start with the simplest clue, the one that first made the modern story unavoidable. Distant galaxies show redshift that grows with distance, as spectral lines slide toward longer wavelengths. The Hubble, Lemaitre law, links that redshift to cosmic expansion, and it does so with a striking regularity across directions. Space is stretching, carrying clusters apart, and the pattern is consistent across the sky. The farther we look, the earlier we see, and the denser the past becomes. Historically, this was not a single discovery but a convergence of ideas. In the 1920s, Edwin Hubble measured galaxy distances using Cepheid variable stars, while Georges Lemaitre connected the observations to expanding solutions of Einstein's equations. The result was unsettling because it implied a changing cosmos, not a static one held up by philosophical preference. Even Einstein had once introduced a cosmological constant to keep the universe still. The sky, however, refused to cooperate. Expansion alone could be a trick of motion, but it is not alone. There is a faint microwave glow coming from every direction, a near-uniform bath of photons at about 2.7 Kelvin. It has an almost perfect blackbody spectrum, the signature of matter and radiation once in thermal equilibrium. That glow is the cosmic microwave background, the cooled afterimage of a time when the universe was opaque. In visuals, it is a soft, all-sky fog, ancient light stretched thin by billions of years of expansion. The reason it exists is both simple and profound. Early on, the universe was a plasma of electrons, protons, and photons, where light scattered constantly and could not travel far. As expansion cooled the plasma, electrons combined with nuclei in a process called recombination, forming neutral atoms. Photons then decoupled from matter and began free streaming through space, carrying a snapshot of that era. When we detect the CMB, we are seeing a surface of last scattering, not a wall in space, but a moment in time. The CMB is not perfectly uniform, and that matters. Tiny anisotropies, temperature differences of only tens of microkelvin, map small density variations in the early plasma. Those variations later grew into galaxies and clusters through gravity, amplified over cosmic time like ripples becoming waves. Their statistical pattern matches a universe that expanded from a simpler, hotter state, and it also encodes the contents of the cosmos. Peaks in the anisotropy power spectrum reveal baryons, dark matter, and the geometry of space, as if the universe left us an acoustic fingerprint. A third clue is written in the lightest atoms, and it is written with unusual precision. Hydrogen and helium dominate, with traces of deuterium and lithium, and the ratios are not arbitrary. Big Bang nuclear synthesis predicts these abundances from early temperatures and densities, when the universe was minutes old and nuclear reactions briefly ran. As it expanded, it cooled too fast for heavy elements to form, leaving stellar furnaces to do that work later. The predictions match observations well enough to make the early universe story hard to dismiss. There is a quiet elegance in how these pillars interlock. Expansion sets the cooling rate sets nuclear outcomes, and the relic radiation preserves the thermal history. If any one piece were badly wrong, the others would not align so cleanly. Yet these pillars do not say everything, and they do not say what people assume. They do not claim a literal beginning from absolute nothing. They do not describe a blast wave expanding into pre-existing space. They describe the evolution of space-time and contents from conditions we can infer. When people say the Big Bang explains creation, they usually mean it explains the earliest chapter we can test with data. That chapter begins when the universe was hot enough for nuclear reactions and dense enough for radiation to dominate. It continues through recombination, when atoms formed and light finally travelled freely. It ends in the sky we can still measure, where galaxies trace the grown-up version of those early fluctuations. The Big Bang model is powerful because it turns the night sky into a laboratory record. Push the equations earlier, and the language gets slippery. General relativity links matter and energy to the curvature of spacetime, and it does so through field equations that are remarkably successful on cosmic scales. Run that framework backward, and densities rise without bound, while characteristic length scales shrink. In many solutions, time seems to hit a boundary where curvature diverges. That boundary is called a singularity. A singularity sounds like an answer, but it is usually a warning sign painted onto the edge of a map. It often means the theory is being used outside its domain, where neglected effects become dominant. Relativity ignores quantum behavior of space-time, and quantum effects should matter at extreme densities. The singularity may mark not the birth of reality, but the breakdown of our description. It's the point where our best classical tool insists on giving nonsense. This is where the documentary's central mystery begins, and it is more subtle than it first appears. There is a difference between a beginning in time and the beginning of time, and the difference changes what questions even mean. A beginning in time is an event with earlier moments behind it, like the first frame of a known reel. The beginning of time would mean there is no earlier, even in principle, because the notion of earlier has no foothold. The phrase before the Big Bang smuggles in an assumption, and it is an assumption our brains make effortlessly. It assumes time is a container that exists independently of the universe, like a stage waiting in darkness. In relativity, time is part of the dynamical geometry, not a background clock. If space-time itself emerges, then asking what happened before may be like asking what is north of the North Pole. The grammar is familiar, but the physics may not permit the question. Yet the analogy may be too neat, and that is part of the tension that keeps the mystery alive. Physics has examples where a boundary in one description becomes a passage in a deeper one, and the edge turns out to be an artifact. A coordinate singularity can vanish when you choose better coordinates, as happens at a black hole horizon. A classical breakdown can dissolve when quantum rules take over, replacing infinities with finite probabilistic structure. The universe has fooled us before with false cliffs, so we face two competing instincts, and each has a respectable mathematical backbone. One says the question is meaningless because time begins with the Big Bang, so before is a category error. The other says the question is meaningful because our current description is incomplete, and the singularity is a placeholder for missing physics. Both instincts can be defended with serious mathematics, and both can mislead when turned into slogans. To see why, we need to separate observation from extrapolation, and then watch where the bridge starts to sway. Observations anchor us to the CMB, element abundances and large-scale structure, all measured with instruments and error bars. Extrapolation carries us to earlier times by trusting the same laws beyond the tested regime. The farther back we extrapolate, the more we gamble, because new physics can enter without warning. Near the earliest instance, energy scales approach the Planck regime, where quantum fluctuations of space-time itself are expected to matter. The Planck time is unimaginably small, and it marks a frontier where our familiar concepts blur. We do not yet have a tested theory of quantum gravity, only candidate frameworks and partial results. Without it, the phrase first moment may be a placeholder, not a fact. The crime scene has tape around it, and we cannot yet cross the line. Even the word nothing becomes unstable under scrutiny, because physics uses the term differently than everyday speech. In ordinary language, nothing means no matter, no energy, no space, no time, and no laws lurking in the background. In physics, the closest thing is often a vacuum state, and a vacuum is not empty. It can contain fields, symmetries, and fluctuations constrained by laws, even when no particles are present. The emptiness still has properties, and properties can have consequences. Quantum field theory predicts that vacuum states have structure, and the structure is not merely philosophical. They can have zero-point energy and correlations, which are measurable in effects like the Casimir force between closely spaced plates. They can produce particles in the presence of horizons or changing backgrounds, as in Hawking radiation and the Unruh effect. The vacuum can behave like a medium with measurable consequences, even though it looks like nothing to our senses. The emptiness, in other words, is busy. This is where the disturbing idea enters, quietly at first, and then with increasing insistence. Multiple independent lines of theory suggest that absolute nothingness is not a stable option, or may not even be definable without contradiction. Some suggest it is impossible to define without already assuming laws in a stage, which means nothing is not a neutral starting point. Others suggest that if a vacuum exists, it can nucleate events, because quantum mechanics allows transitions that classical intuition forbids. The question shifts from why is there something to could nothing persist? One proposal imagines the universe tunneling into existence, borrowing the quantum idea that systems can cross barriers without climbing over them. Another imagines a quantum fluctuation giving rise to a tiny expanding region, a seed that inflates into a cosmos. These ideas use the language of quantum mechanics, where probabilities can assign weight to classically forbidden transitions. They do not yet have decisive observational support, but they sharpen the question. If the universe began as a quantum event, what counts as an initial condition? Inflation adds another layer, and it does so with dramatic visual consequences. It proposes a brief era of accelerated expansion that smooths the universe and seeds structure, stretching microscopic fluctuations to astronomical scales. Inflation helps explain why the CMB is so uniform across regions that seem causally disconnected in a simple expansion picture. It also predicts a spectrum of primordial perturbations that matches what we see, including the near-scale invariance of fluctuations. In the mind's eye, it is a rapid unfurling, space itself swelling faster than light can cross it. But inflation raises its own origin problem, and it refuses to stay politely in the background. What started inflation, and what set its initial conditions, and why did it end where it did? Many inflation models imply that inflation can be eternal in some regions, even if it ends locally. That leads naturally to a multiverse picture, where many bubble universes form within a larger inflating background. The same mechanism that explains smoothness can also multiply realities. A multiverse is not a punchline, it is a consequence in some equations, and that is precisely why it is controversial. It also tests the boundary between physics and metaphysics, because the usual standard is observational access. If other regions are causally disconnected, evidence becomes indirect and statistical, inferred from what inflation tends to produce. The question becomes whether a theory can be scientific without direct access, or whether it must offer signatures within our horizon. We are forced to ask what counts as evidence when the stage extends beyond the visible. Cyclic and bouncing cosmologies offer a different escape route, and they do it by reinterpreting what beginning means. Instead of a beginning, the universe could have had a prior phase that contracted, with a bounce replacing the singularity. A bounce could replace the singularity with a transition governed by new physics, perhaps quantum gravitational pressure or modified dynamics. In that case, before the Big Bang could mean before the hot expansion, not before time. The arrow points through the boundary rather than stopping at it. These models face hard constraints, and they face them under the unforgiving light of data. They must reproduce the observed CMB spectrum and element abundances, not just qualitatively, but quantitatively. They must avoid instabilities that would destroy the smoothness we observe, because contraction can amplify irregularities. They must explain entropy growth across cycles, or else explain why entropy resets, because thermodynamics is not easily negotiated. If the universe repeats, what prevents the past from piling up into disorder? Quantum gravity approaches try to address the singularity directly, treating it as a clue rather than a wall. Loop quantum cosmology suggests discrete spacetime can produce a bounce, with quantum geometry acting like a repulsive effect at extreme density. String theory offers scenarios with extra dimensions and branes, where collisions could mimic a hot beginning without a classical singularity. Other approaches treat spacetime as emergent from entanglement or deeper algebraic structure, where geometry is not fundamental but derived. Each approach changes what before might mean. None of these frameworks is yet the final story, and the uncertainty is part of the honest narration. Each offers a different answer to what existed before everything, and each pays a price in assumptions. Some replace before with a different parameter, like a Euclidean time or a quantum state. Some replace nothing with a field, a vacuum, or a landscape of possibilities. The options are not just different answers, they are different definitions of the question. The unsettling thread is that the universe may not have begun from absolute emptiness, even if it had a beginning of some kind. If laws exist, they already impose structure, because laws constrain what can happen and what cannot. If quantum fields exist, they already provide a substrate, even when no particles are excited. If time emerges, the question of before becomes a category error that our brains keep making. We keep reaching for a calendar where there may be none. So what do cosmologists actually claim today, when they speak carefully and stick to what can be defended? They claim the hot Big Bang describes a well-tested early phase, supported by multiple independent observations. They claim the universe has expanded and cooled from that phase, leaving measurable relics in radiation and matter. They claim our best classical theory predicts a boundary, and that boundary likely signals missing physics. The confidence is real, but it is bounded. They do not claim to have witnessed the first instant, because no telescope can see through the opaque plasma before recombination. They do not claim that nothingness is a measured initial condition, because nothing is not an observable state in the usual sense. They do not claim that the word before has a clear meaning at the edge of space-time, because meaning depends on the structure of time itself. They claim that the evidence points to a story, and the story has a gap. The gap is where mystery lives. That gap is not just a missing page, it may be a missing concept, and that is what makes it so difficult to close. If time is part of the system, then the system cannot be placed inside time like an object on a shelf. If the universe is all physical reality, then there is no external stage to stand on, no outside clock to consult. The question becomes whether explanation requires an outside, or whether explanation can be internal and self-contained. At the boundary, even common sense becomes a hypothesis. Still, the human mind keeps returning to the same pressure point, as if it were a bruise we cannot stop touching. If there was a beginning, why that beginning rather than none, and why those laws rather than others? If there was no beginning, how can an infinite past be coherent, and what does infinite mean for physical processes? If nothing is unstable, what does that say about the idea of non-existence, and about our intuition that absence is the default? Perhaps the deepest clue is not an answer, but the persistence of the question. This chapter sets the rules for the investigation, because mysteries collapse when we stop respecting evidence. We will treat the Big Bang as a successful model, not a mythic origin story dressed in equations. We will separate what is observed from what is inferred, and we will label the inferences honestly. We will follow theories only as far as they remain testable, and we will mark where they become speculative. The crime scene is real, but the suspect list is long. Next, we move from the crime scene to the suspects. We will examine the quantum vacuum and tunneling proposals, then inflation and its consequences, including the uncomfortable logic of eternal expansion. We will test cyclic and multiverse ideas against the data we actually have, not the data we wish we had. Finally, we will confront quantum gravity, where time itself may be an emergent clue, and where the word before may finally lose its grip. Chapter 1 left us at a boundary where our language fails before our curiosity does, and that mismatch is not accidental. We now follow the evidence into the physics of nothing, because cosmology keeps pointing there, again and again, whenever we push the equations toward the beginning. The closer we get to that edge, the more our ordinary nouns start to wobble, as if reality is refusing to fit inside them. In everyday speech, empty space means absence, a cleared stage with no actors and no props. In modern physics, empty space is a state, and states can carry structure, constraints, and even a kind of restless bookkeeping. When the camera drifts across a dark interstellar void, the darkness looks calm, yet our best theories insist it is not inert. Even the blackest regions, far from stars, are threaded with fields that cannot be switched off. The shift begins with quantum field theory, a framework built in the 20th century to make quantum mechanics compatible with special relativity. It flips the intuition that particles are the basic ingredients, because the fundamental entities are fields that exist everywhere, even where no particles appear. A field is not merely a mathematical trick, it is a physical quantity assigned to every point in space-time, like a temperature map that never stops existing. Historically, this was a hard-won synthesis. Dirac, Feynman, Schwinger and Tomonaga helped build a language where creation and annihilation are operators, not miracles. A particle in this picture is an excitation of a field, like a ripple that can be counted and tracked. The electron is not a tiny bead moving through void, but a pattern in an electron field, localized, quantized, and able to transfer energy in discrete lumps. When detectors click, they are not catching marbles, they are registering field excitations interacting with matter. The click is a macroscopic event, but it begins as a microscopic coupling between a field and a device built from atoms. The same logic applies to photons, quarks, and every species we know how to describe, even the ones we only infer indirectly. The universe is less like a box of objects and more like overlapping continuous ingredients, each with its own rules for how it can vibrate. Visually, imagine transparent sheets layered through space, each sheet capable of rippling in its own characteristic way. Some ripples can travel freely, while others are confined, bound, or screened by the environment. So what is the vacuum in this picture? If fields are everywhere and never truly vanish, It is not the absence of fields, but the lowest energy configuration of those fields, given the circumstances and the geometry. The vacuum is a ground state, a technical phrase that sounds quiet, yet it hides a precise meaning. It is the state with no excitations above the minimum allowed energy, and crucially, that minimum is not chosen by taste, because it is fixed by the quantum structure of the theory. Lowest energy does not mean zero activity in the classical sense, where a pendulum can hang motionless forever. Quantum systems cannot be pinned to perfect stillness without paying a price, because the very act of fixing one quantity sharpens uncertainty in another. The vacuum is quiet only in the way a sleeping city is quiet. Patterns remain, and the possibility of motion is built in. If you could zoom in far enough, the stillness would look less like silence and more like constrained motion. The reason is built into the uncertainty relations, which limit how precisely certain pairs of quantities can be fixed at the same time. For a simple particle, position and momentum refuse to be simultaneously exact, and for fields there is an analogous pairing between the field value and its conjugate momentum. If a field were exactly still everywhere, its conjugate quantity would become infinitely uncertain, and the theory would contradict itself. The vacuum is therefore not a frozen configuration, but a delicately balanced compromise enforced by quantum rules. A useful analogy is a mass on a spring that can never sit perfectly at rest, even when cooled as far as nature allows. Even at the lowest allowed energy, it retains a residual jitter that cannot be removed, because removing it would require forbidden precision. In the lab, this is not poetry. It is the reason atoms do not collapse into classical stillness. It is also why even ground state atoms still have measurable motion, which shows up as spectral line widths and quantum noise. In quantum field theory, each mode of a field behaves like such an oscillator, and mode here means a particular wavelength and frequency pattern. Space becomes a kind of resonant instrument, and the field can vibrate in harmonics that depend on the environment. Add up all those modes and the vacuum becomes a complicated ground state, not a blank page, and not a simple zero. The number of modes is effectively infinite, which is why the vacuum's bookkeeping becomes both powerful and dangerous. This is where the phrase zero-point energy enters, and it sounds like a loophole if you hear it too quickly. It is the irreducible energy of the ground state, present even when no particles are detected, and it is not optional within the formalism. The point in 0 point is the bottom of the ladder, the lowest rung that cannot be stepped below. In the oscillator picture, it is the half quantum that remains when every removable quantum has been taken away. Vacuum fluctuations are the time-dependent variations in these fields around the ground state, and the phrase can mislead if we imagine tiny objects flickering in and out. They are not little particles popping in and out as literal objects, but changes in field correlations, the statistical texture of the vacuum. In quantum language, the vacuum has a spread in possible values, even when its average is stable. What fluctuates is not a classical field value you could photograph, but the outcomes you would obtain if you probed the vacuum repeatedly. The popular story of pairs appearing and vanishing is a metaphor that can be useful, but it can also trap the imagination. The deeper statement is that the vacuum has non-zero variance and measurable effects, meaning the vacuum is not a single number, but a distribution of possibilities. What matters is not a cartoon of borrowed energy, but the measurable consequences of quantum fields constrained by reality. In practice, those consequences show up as tiny shifts in atomic energy levels and forces that persist even when everything is neutral. If this seems like wordplay, physics offers a test that pushes back with numbers and apparatus. The vacuum can exert forces when boundaries change what field modes are allowed, and this is where nothing becomes something an engineer can manipulate. When we put metal surfaces close together, we're not adding matter to the gap. We are sculpting the allowed patterns of a field. The emptiness becomes a cavity with rules, and the rules have mechanical consequences. The Casimir effect is the cleanest example that nothing can be engineered, and it has been tested in increasingly precise experiments since the late 20th century. Place two uncharged conducting plates very close together, and they attract as if an invisible pressure is pushing them inward. In a clean vacuum chamber, with the plates aligned like mirror-dark doors, the force is small but stubborn. The closer the plates, the stronger the pull, rising rapidly at separations measured in micrometers and below. The attraction is not because the plates create new matter between them, and it is not an electrostatic trick if the experiment is done carefully. It is because the plates impose boundary conditions that reshape the vacuum modes, and boundary conditions are physical constraints, not philosophical choices. Conductors force the electromagnetic field to vanish in certain ways at their surfaces, and that restriction matters. In the visuals, the gap becomes a narrow corridor where only certain standing waves can survive. Between the plates, only certain wavelengths of the electromagnetic field fit, like standing waves on a string pinned at both ends. Outside, a larger set of modes exists, and the difference in vacuum energy produces a net pressure that nudges the plates together. The vacuum, in other words, responds to geometry, and geometry becomes a handle on empty space. It is a quiet demonstration that the vacuum is not merely there, but there under constraints. The key point is not that we have bottled nothingness, as if vacuum were a substance captured in a jar. The key point is that the vacuum behaves like a physical state whose properties depend on constraints, and constraints can be changed. When the plates move, the allowed modes shift, and the energy bookkeeping shifts with them, quietly but measurably. In modern experiments, researchers must also subtract ordinary forces because the Casimir signal is delicate and easy to contaminate. Casimir forces are small, but they are real and measured, and they now matter in micro and nanoscale devices. At tiny separations, the force can compete with mechanical supports, reminding engineers that quantum vacuum effects are not confined to blackboards. It is a subtle lesson. Empty space becomes more active as we probe smaller distances and tighter boundaries. The vacuum is not a background. It is part of the system, and miniaturization makes that impossible to ignore. Once the vacuum is a state, a new question appears, and it feels almost like a trapdoor opening under the word empty. Which vacuum are we talking about, and who gets to decide what counts as empty in a changing universe? The answer is not a matter of taste, because the mathematics of fields makes the choice depend on space-time and motion. Even the act of defining no particles depends on how you decompose the field into modes. In flat space-time with inertial observers, quantum field theory defines a natural ground state, often called the Minkowski vacuum. It is the state that looks empty to observers who move at constant velocity, and it respects the symmetries of special relativity. In that setting, the decomposition into positive and negative frequencies is clean, and no particles is a stable statement. This is the vacuum that underwrites ordinary particle physics, where accelerators and detectors can agree on what counts as an excitation. But in curved space-time, or for accelerated observers, the definition can change, and the change is not a semantic trick. This is not philosophical relativism, it is a mathematical fact about how fields are decomposed into modes, and modes are tied to time. Different observers slice space-time differently, and they disagree about what is a particle, because they disagree about what counts as time translation. When time is not globally uniform, the very idea of a universal energy spectrum starts to fracture. A particle, in this technical sense, is associated with a particular notion of energy, and energy depends on how you define time. In a static space-time, there is a preferred time symmetry, and energy conservation follows neatly. In a dynamical space-time, the symmetry can be absent, and the vacuum becomes less like a fixed floor and more like a shifting reference level. The field can be in a perfectly well-defined state, yet different observers will expand it into different sets of excitations. The Unruh effect is the simplest shock to classical intuition, and it is one of the clearest demonstrations that particle content is not absolute. An observer accelerating through what an inertial observer calls vacuum will detect a thermal bath as if the emptiness were warm. The accelerating observer's detector clicks with a distribution that matches a temperature, even though nothing heated up in the usual sense. The temperature is proportional to acceleration, which makes the idea crisp, even if the measurement is brutally difficult. Nothing in the local laws changes, and no physical furnace is switched on behind the scenes. The difference comes from the observer's horizon and the way acceleration partitions field modes, cutting space-time into regions that cannot communicate. Acceleration creates a boundary of access, and the vacuum, when restricted to what the observer can see, looks like a mixed thermal state. In visuals, the world line of the observer becomes a bright curve, and the horizon appears like a diagonal veil that hides part of space-time. The temperature is tiny for everyday accelerations, so it is hard to measure directly, and that is why the effect remains mostly a conceptual landmark. Yet the effect is a clue that particle content is not an absolute property of the vacuum. and it warns us against treating no particles as a universal statement. The vacuum is not just what is there, but what can be observed under specific conditions. It invites a quiet question. If emptiness can look warm, what else can it look like under extreme motion? Black holes raise the stakes because they create horizons without rockets, and horizons are the key ingredient in this strange thermality. Hawking radiation predicts that black holes are not perfectly black, but emit particles and slowly lose mass, a claim that reshaped theoretical physics in the 1970s. The idea is unsettling because it makes gravity behave like a thermodynamic system, with temperature and entropy. Historically, it also forced physicists to confront a new triangle of ideas: quantum theory, space-time geometry, and information. The simplified picture again uses pairs near the horizon, with one escaping and one falling in, and it persists because it is easy to visualize. The deeper statement is that curved space-time mixes positive and negative frequency modes, so what counts as vacuum in one region does not match what counts as vacuum in another. The horizon is not a physical wall, but it is a causal divider, and the field responds to that divider. The radiation is not a special substance near the edge, but a global accounting effect tied to how states are defined across space-time. To a distant observer, the vacuum near the horizon is not the same as the vacuum far away, even if the field is in a smooth state for someone falling in. The horizon changes what counts as a ground state, and the field responds by producing a flux that looks like radiation at infinity. In the visuals, the black hole is a dark disk, yet the mathematics paints a faint, steady glow around its edge. That glow is unimaginably cold for stellar black holes, but conceptually it burns with significance. Hawking's result ties quantum theory, gravity, and thermodynamics into one equation, and the unity is as important as the prediction. It says that horizons carry temperature and entropy, and that empty space near them is active, structured, and constrained. When a black hole radiates, it is not creating matter from literal nothing, but converting the field's quantum state into detectable excitations in a curved background. The vacuum becomes a participant in the story of evaporation, not a passive backdrop. This matters for our central question because the early universe is not flat and calm, and it is not even approximately static. It is a rapidly evolving space-time, dense and hot, with expansion that changes the meaning of time and energy as the cosmos unfolds. If horizons and acceleration can make vacuum look different, then cosmic expansion can do something similar on the larger scale. The early cosmos is, in effect, a laboratory where the background itself is the experiment. In cosmology, expansion can amplify vacuum fluctuations and convert them into real excitations, and this is not a metaphor but a calculable effect. The same mechanism that seeds structure in inflation uses the fact that the vacuum is not inert, and that quantum fluctuations can be stretched to astronomical sizes. What begins as microscopic uncertainty becomes macroscopic pattern, like a faint grain in an image magnified until it becomes visible structure. In the visuals, tiny ripples on a field grid elongate, then freeze into long wavelength bands that later guide matter. The idea is subtle because the vacuum fluctuations do not start as classical lumps, and they do not carry a definite shape until the expansion freezes them in. As space expands, wavelengths can be pulled beyond a horizon scale, and their oscillations effectively stop, leaving behind a record in the field. Later, when the universe cools and matter forms, those patterns become the scaffolding for galaxies and clusters. The cosmic microwave background becomes a kind of photograph of this process, with temperature speckles tracing primordial fluctuations. So, nothing is already split into categories, and the split is not philosophical but operational. There is the vacuum of a field in a given geometry, and there is the observer-dependent notion of particles riding on that vacuum. A vacuum state can be well-defined, yet what counts as a particle can change with motion, curvature, and the availability of a global time coordinate. The deeper lesson is that emptiness is not a single condition, but a relationship between a state and an observer. If the vacuum depends on space-time, then the vacuum cannot be defined without specifying the stage, and that stage is part of the physical system. In general relativity, space-time is not a neutral container, because it bends and evolves in response to energy and pressure. The vacuum, therefore, is not what remains when you remove everything, but what the fields settle into given the geometry. This is where the narration's mood darkens, because the vacuum starts to tug on the very arena it lives in. At this point, the story turns from strange to disturbing, because the vacuum is not merely a curiosity of quantum theory. If the vacuum is a physical state with energy, then vacuum energy should gravitate, and gravity is not forgiving about where energy comes from. In Einstein's theory, energy density and pressure both contribute to curvature, and uniform energy has an especially dramatic effect. A uniform vacuum energy behaves like a negative pressure, which is precisely the ingredient that can drive accelerated expansion. General relativity does not care whether energy comes from particles or from a ground state, because the equations respond to the stress-energy tensor. Energy and pressure curve spacetime, and a uniform vacuum energy looks like a cosmological constant, a term that acts the same everywhere. A constant vacuum energy does not dilute as space expands, and that persistence makes it cosmologically powerful. In plain language, it is an energy that does not thin out, even as the universe grows. Einstein once introduced a cosmological constant for a different reason, to hold the universe static, because the prevailing view at the time favoured an eternal cosmos. When expansion was discovered, he reportedly regretted the move, though the history is more nuanced than the legend suggests. Today, a small positive effective cosmological constant fits the observed accelerated expansion, and the term returned from exile with new authority. The constant went from an ad hoc patch to a central parameter, and that reversal still feels like a plot twist. We call that acceleration dark energy because we do not know its microphysical origin, and the name is an admission of ignorance rather than a solution. Observationally, it behaves like a nearly constant energy density filling space, pushing the expansion to speed up rather than slow down. In the visuals, distant galaxies drift apart, and the separation rate increases, as if space itself has a quiet pressure. The effect is subtle nearby, but over billions of years it reshapes the cosmic future. Here, the vacuum becomes a crisis rather than a curiosity, because naive quantum field theory estimates of vacuum energy are catastrophically larger than what cosmology measures. If we sum zero-point energies up to a high cutoff scale, the predicted density is enormous, and the number is not merely a bit off. Depending on the cutoff, it overshoots the observed value by many orders of magnitude, making the mismatch one of the worst in physics. It is as if the equations insist the universe should be violently curved, while the sky insists on calmness. The exact number depends on assumptions, and responsible physicists argue about which assumptions are justified. Yet the mismatch is the headline, because even conservative choices tend to produce a value that is absurdly large compared to the gentle dark energy we infer. The universe is not curled up by a gigantic vacuum energy, yet the simplest calculation says it should be, and that contradiction demands explanation. Why does the vacuum gravitate so weakly? Or why do the contributions cancel so precisely, when nothing in the naive math enforces it? This is the cosmological constant problem, and it is not a bookkeeping error that can be fixed with a clever unit conversion. It is a sign that our understanding of nothing is incomplete, or that we are missing a principle that cancels contributions with extraordinary precision. The vacuum, which should have been the simplest state, becomes a mirror reflecting the limits of our frameworks. It is also a reminder that quantum field theory was built to predict scattering and spectra, not to set the curvature of the entire universe. Some possibilities invoke symmetry, like supersymmetry, which could cancel bosonic and fermionic vacuum energies because their contributions come with opposite signs. In an exact supersymmetric world, the vacuum energy could naturally be small, because every mode would have a partner that balances it. But supersymmetry, if it exists, is broken at accessible energies, and the cancellation is not exact, leaving the problem largely intact. The idea remains compelling because it would make the smallness less mysterious, yet nature has not handed us the missing partners. Other approaches treat vacuum energy as renormalized away, and renormalization is a standard tool in quantum field theory. In non-gravitational physics, only energy differences matter, so shifting the zero of energy is harmless, like choosing sea level for altitude. Yet gravity makes that move dangerous, because space-time curvature responds to absolute energy density, not merely to differences we can ignore. The vacuum is therefore a place where two successful theories meet, and fail to speak the same numerical language. Some proposals shift the problem into dynamics, where the vacuum energy relaxes to a small value through the evolution of fields. Others suggest selection effects, where many vacua exist and we observe one compatible with galaxies, because observers require structure. None of these resolutions is universally accepted, and that uncertainty is part of the tension that hangs over modern cosmology. The unsettling observation is that we can measure dark energy's effect on expansion, yet we cannot explain its scale from first principles. The vacuum is both the simplest state and the least understood ingredient in the cosmic budget, which is an uncomfortable combination. The disturbing implication is not merely that empty space has energy, but that our best frameworks cannot agree on how that energy should appear in the real universe. We can calculate vacuum effects in the lab with exquisite precision, yet we cannot reconcile the vacuum with the sky. It is a crack that runs through the foundations, thin but persistent. So the vacuum is not one thing, and it cannot be summarized as a single, universal nothing. It is a ground state defined by fields, by geometry, by boundary conditions, and by the observer's motion, each layer adding its own definition. When we say vacuum, we are compressing a long list of assumptions into one short word. That compression is useful for equations, but it can be misleading for intuition. This turns nothing into a layered concept, with technical meaning that differs from the philosophical ideal of absolute absence. Absolute nothingness would mean no fields, no laws, no space-time, and no state to define, which is so empty that physics cannot even begin. Physics rarely speaks about that absolute nothingness because it has no handle on it, and no experiment can reach it. Even our best empty chambers still presuppose a space-time arena and the quantum rules that govern it. The vacuum is already something, and it is the closest operational notion we can test, manipulate, and measure. It is what remains when we remove particles, cool systems toward their ground state, and isolate regions from external disturbances. Even then, the vacuum retains correlations, constraints, and a minimal energy that cannot be eliminated. In visuals, the lab vacuum chamber looks pristine, yet the narration reminds us that pristine is not the same as nothing. Now we can sharpen the central question without hiding behind words and without pretending that nothing is a single concept. If the vacuum is a physical state, then what existed before may reduce to which vacuum, which fields and which rules, rather than a literal absence. The question becomes less about emptiness and more about state, stability, and change. And once you ask about stability, you are forced to ask what could disturb it. The early universe could then be described as a change of state, rather than a creation event, and that shift in framing matters. A phase transition can turn one vacuum into another, releasing energy and changing symmetries, and phase transitions are familiar in the everyday world. Water freezes, magnets align, and superconductors switch on, each time reorganizing the ground state of a system. In each case, the nothing happening state is actually a structured minimum, and the structure can rearrange abruptly. We already know phase transitions in the laboratory, where cooling can reorganize a system's ground state and produce new collective behavior. In particle physics, similar transitions could have happened as the universe expanded and cooled, because temperature affects which symmetries are favored. As the cosmic plasma thinned, fields could have settled into new configurations, selecting the rules that govern particles today. The vacuum in this sense is not only a background, but also a historical record of what the universe has cooled through. In that view, a hot Big Bang could be the aftermath of a vacuum instability, a release of stored energy from a higher energy state. A false vacuum could decay, or a high-energy symmetric phase could break into the lower energy structure we inhabit, and the released energy would appear as heat and particles. The bang, then, is not necessarily a moment of creation, but a moment of conversion. Visually, the transition is not a spark in empty darkness, but a reshaping of an all-pervading field, like a landscape snapping into a new contour. This does not yet answer why there are fields and laws at all, and it does not dissolve the deeper mystery. But it reframes the question from creation out of nothing to evolution from a prior ground state, which is a question physics can at least attempt to model. The emphasis shifts from metaphysics to dynamics, from why anything to why this state. That shift is modest, yet it is the difference between an unaskable question and a calculable one. It also changes what before might mean, and it forces us to treat time with caution. Before could refer to an earlier phase of fields, even if classical time behaves strangely near the boundary, and even if our usual clocks fail. If space-time itself is evolving, then before may not be a simple arrow pointing into a pre-existing emptiness. The word may still be useful, but it becomes a label for ordering, not a guarantee of a familiar timeline. We should be careful with the word create. because quantum field theory often means create particles, not create existence. Particle creation in curved space-time is a conversion of vacuum correlations into detectable excitations triggered by changing geometry or horizons. The vacuum is not an empty container that suddenly fills, but a state whose definition shifts as the background shifts. The drama is in the changing notion of what counts as positive frequency, which is the technical heart of why particles appear. Even in Hawking radiation, the black hole does not summon matter from a literal void, as if it were conjuring substance from nothing. It transforms the quantum state of fields in a geometry with a horizon, and the transformation has a thermal signature. The radiation is a message about the vacuum under extreme conditions, not a loophole in conservation laws. The black hole pays the bill with its mass, and the accounting remains strict, even when the mechanism feels uncanny. So the vacuum is not a loophole that lets us say something came from nothing, and it is not a rhetorical escape hatch. It is a reminder that our intuitive nothing was never a physical concept to begin with, because physics begins with fields, states, and rules. When we say vacuum, we are already inside a framework that assumes a great deal. The mystery is not erased, but it is relocated from empty space to the origin and selection of the framework itself. The chapter's tension comes from a simple inversion, and it is worth lingering on the reversal. If empty space is a structured state, then the default is not absence. It is a ground state with rules, correlations, and constraints. The zero of the universe is not blank, it is patterned, and the patterns have consequences. The more carefully we define zero, the more it behaves like a physical object with properties. That raises a question that sounds almost theological but is sharply physical, because it asks about the permanence of the substrate. Were the fields always there, or are fields themselves emergent from something deeper, something that only looks like a field at low energies? The question is not about purpose, but about ontology within physics, what the theory treats as fundamental. And it carries a quieter question. If fields emerge, what does their vacuum emerge from? If fields were always there, then before everything might mean before our particles and stars, not before the substrate that allows particles and stars to exist. If fields are emergent, then the vacuum is a surface layer over a deeper theory, and our nothing is already a kind of foam on top of hidden structure. Either way, the vacuum refuses to behave like a clean starting point. It behaves like a minimum of a landscape that we do not yet fully see. It behaves like a system with measurable consequences, and with unresolved bookkeeping that affects the fate of the cosmos, which is why the subject feels unsettling. This is why scientists call the quantum vacuum strange, and why some call it disturbing, because it suggests that the closest thing to nothing is already full. It is full of constraints, correlations, and energy, and it is full of unanswered questions about how those quantities gravitate. The emptiness between galaxies becomes, paradoxically, one of the most consequential ingredients in the universe. Push the equations earlier, and the language gets slippery, because the vacuum depends on the stage. Yet the stage itself may be part of what we are trying to explain, and that circularity is where cosmology becomes philosophical without losing its mathematics. We're trying to define the ground state of a system whose arena is also dynamical. The vacuum is a state of fields, but the fields help determine the geometry, and the geometry helps define the vacuum, an interlock that feels almost like a riddle. Next, we follow this idea into the early universe as a dynamical vacuum. We ask whether the Big Bang could be a transition, and whether nothing could ever be stable, even in principle. We also ask what it would mean for a vacuum to be metastable, perched above a lower energy state like a ball balanced in a shallow dip. In visuals, the ball trembles, and the landscape beneath it hints at deeper valleys that cannot yet be seen. We will carry forward 3 anchors that matter for the rest of the investigation, because they keep the mystery tied to testable physics. Quantum fields treat particles as excitations, so emptiness is a ground state, not a blank, and that ground state can have measurable structure. Vacuum behavior depends on boundaries, motion, and curvature, so empty is not universal, and observers can disagree about what they detect. Vacuum energy also collides with cosmology, so our accounting of nothing is unfinished, and the mismatch is not a minor technicality. If the universe began, it may have begun inside a pre-existing structure of laws and fields, even if those laws later changed form. The deepest mystery may not be what happened before the beginning, but why any rules exist at all, and why the vacuum is the way it is. Chapter 2 left us with a vacuum that is structured, energetic, and not obviously stable. In quantum field theory, empty space is never truly empty. It is a restless baseline with fluctuations and latent energy. If nothing can carry pressure and energy, then the early universe may have been driven by a vacuum-like state. That possibility leads to inflation, the leading framework for the first fractions of a second. Inflation begins as a pragmatic move, not a metaphysical claim about ultimate origins. It was proposed to repair specific cracks in the standard hot Big Bang story, using the tools of general relativity and field theory. It is an era of accelerated expansion, extremely early, extremely brief, and cosmologically decisive. The idea is simple in outline, yet it rewires what beginning can mean. Instead of starting with a hot fireball everywhere at once, the universe may start by stretching a small prepared region into something vast. Visually, imagine the early cosmos as a dark stage before the lights come up. There is no familiar matter yet, no atoms, not even stable particles in the everyday sense. There is only an evolving space-time geometry and a field configuration that acts like a temporary vacuum. The camera pulls back and the stage itself grows, space multiplying faster than intuition can track. Start with the puzzles that the hot Big Bang model does not naturally solve. The Big Bang describes a hot, expanding plasma, then cooling, then atoms, then the cosmic microwave background. It is a remarkably successful thermal history, and it predicts light element abundances and the CMB with impressive accuracy. But when we run that expansion backward without inflation, the initial conditions look strangely tuned. The equations do not forbid those conditions, yet they make them feel like an unlikely coincidence. The first puzzle is the horizon problem, which is really a problem about causal contact. Causal here means something plain. Can one region influence another using signals that travel at or below light speed? The CMB temperature is nearly the same in opposite directions of the sky, varying only by about 1 part in 100,000. In a simple, non-inflationary history, those regions were never close enough to exchange light or heat. They were separated too early before there was time for a shared thermal conversation. They look like two rooms that match temperatures without sharing a door. Thermal equilibrium requires interaction, and interaction requires time and communication through particles or radiation. Yet the standard expansion gives too little time for the entire visible universe to equilibrate. We can draw the causal diagram and see it directly. Light cones from opposite sides fail to overlap at early times. So the question is sharp. Why does the sky look like one coherent object, rather than a patchwork of unrelated temperatures? The horizon problem becomes more vivid when we remember what the CMB is. It is not a surface in space, but a moment in time, when the universe cooled enough for electrons and protons to form neutral atoms. Before that, photons scattered constantly off free charges, and space was opaque like a glowing fog. At recombination, the fog thinned, and photons began to stream freely, carrying a snapshot of conditions across the cosmos. That snapshot is astonishingly uniform, and uniformity is what needs explaining. The second puzzle is the flatness problem, which is a problem about geometry and instability. In general relativity, the expansion rate and the spatial curvature are tied to the energy density through the Friedmann equations. Curvature is not a vague shape, but a measurable deviation in how distances and angles behave on large scales. The observed universe is very close to flat, meaning curvature is tiny compared to the expansion scale. That near flatness is not just aesthetic, it is encoded in how the CMB peaks line up and how large-scale structure evolves. Without inflation, that near flatness is not generic, it is precarious. Early on, the density would have needed to sit extraordinarily close to a critical value, with deviations tuned to many decimal places. A slight mismatch in the early universe would have amplified into a strongly curved cosmos by now. In a curved universe, expansion either races away too quickly for galaxies to form, or collapses back before complexity has time. Flatness, in the non-inflationary picture, looks like balancing a pencil on its tip and finding it still standing billions of years later. The third puzzle is the monopole problem, which is a problem about unwanted relics. Many particle physics ideas, especially grand unified theories, predict heavy stable objects produced in early high-temperature phase transitions. These are topological defects, analogous to imperfections that form when a material cools and its symmetry breaks. Magnetic monopoles are the most famous example. hypothetical particles carrying isolated magnetic charge. If those relics were made abundantly, they should still be around, and they should dominate the mass budget. We do not see them, at least not at the predicted levels. That absence could mean the particle physics is wrong, or the cosmology is missing a dilution mechanism. Inflation offers dilution by making space grow so much that relic densities become negligible. It does not need to forbid monopoles outright. It only needs to spread them so thin that our observable region is effectively empty of them. The same logic applies to other heavy defects and unwanted remnants from early symmetry breaking. Historically, these problems sharpened in the late 1970s and early 1980s as cosmology and particle physics began speaking the same language. The hot Big Bang had matured into a precision framework, but it also exposed the fragility of its starting assumptions. Inflation was introduced as a repair that was bold enough to be testable. It was not invented to create a multiverse or to mystify the origin story. It was invented because the universe was behaving as if it had been smoothed, flattened, and cleaned. Inflation's core move is to change the early expansion from decelerating to accelerating. In normal matter or radiation domination, expansion slows because gravity pulls inward, and pressure contributes to gravity as well. In inflation, the energy behaves differently, producing repulsive gravity in the sense of accelerated expansion. This is not anti-gravity in a cartoon sense, but a consequence of Einstein's equations. If the pressure is negative enough, the combination of energy density and pressure drives accelerated growth. General relativity allows this when pressure is sufficiently negative. A nearly constant energy density with negative pressure makes the scale factor accelerate, and in the simplest models that acceleration is close to exponential, space expands so rapidly that distances grow faster than light can cross them, without violating relativity's local speed limit. Nothing outruns light through space in its own neighbourhood. Instead, space itself stretches, and the separation between distant points increases faster than any signal can bridge. In this picture, the early universe is not primarily a hot gas at first. It is dominated by an effective field whose energy is stored like a vacuum. That field is called the inflaton, though its microphysical identity remains unknown. We use the name as a placeholder because the mathematics cares more about the field's energy landscape than about its detailed particle pedigree. The inflaton is the simplest way to package an early vacuum-like state into a dynamical story. The inflaton is best treated as an effective description, not a confirmed particle. It stands in for whatever degrees of freedom drove the accelerated expansion, whether that is a new scalar field or a collective behavior of known physics at extreme energies. The key is its potential energy, which can dominate over kinetic energy for a period. When the field rolls slowly along a shallow potential, its energy density changes only slightly. That slow evolution is why many models are called slow-roll inflation. When potential energy dominates, the inflaton behaves like a false vacuum or vacuum-like state. A false vacuum is a metastable configuration that is not the lowest possible energy, like a ball resting in a shallow dip rather than the deepest valley. It can persist for a while, then decay or roll toward a lower energy state. The word false is not moral, it is technical. It means the state is not the true ground state. In quantum theory, such a state can survive for a long time, yet still be temporary. This vacuum-like state has a crucial property for cosmology. Its energy density stays nearly constant while space expands, unlike matter whose density dilutes as volume grows. That means the total energy in a comoving region grows with volume, which feels paradoxical until we remember gravity's bookkeeping is subtle. In general relativity, energy conservation is local, not global, and the expanding geometry changes what total energy even means. The field can do work on spacetime through its negative pressure, and spacetime responds by expanding faster. Inflation then becomes a machine that takes a small, causally connected patch and stretches it, a region that could equilibrate before inflation becomes enormous afterward, so enormous that it can encompass our entire observable universe. The CMB uniformity is reinterpreted as a memory of that earlier contact. The camera can show it as a tiny patch, almost microscopic by cosmic standards, ballooning into a sphere that dwarfs galaxies. What looks like miraculous coordination becomes the afterimage of a once intimate neighborhood. That is the intuitive fix for the horizon problem. The farthest points we see today were once close enough to share a common thermal history, exchanging radiation and smoothing out differences. Inflation makes them look disconnected now, because it expanded the distances faster than signals could later traverse. After inflation ends, the universe returns to slower expansion, and the horizon grows again. But by then, the uniformity has already been stamped in. Inflation also addresses flatness through geometric dilution. Curvature terms fall rapidly relative to the expansion rate during accelerated growth, because the scale factor grows so quickly that any initial curvature becomes negligible. After enough e-folds of expansion, space looks nearly flat within any region we can observe. An e-fold is a simple unit. Each one means the universe grows by a factor of e, about 2.718. Dozens of e-folds are enough to take a tiny patch and make it look flat to extraordinary precision. The same expansion dilutes unwanted relics. Monopoles and other heavy defects, if produced before inflation or early in it, get spread so thin that they become essentially absent in our observable volume. The absence becomes a prediction rather than an embarrassment. Inflation does not need to destroy relics, it merely needs to make them rare per unit volume. In a universe that is expanded by a stupendous factor, rare becomes effectively never seen. These successes explain why inflation became central, but they are not its most striking feature. Inflation does not only smooth the universe, it also seeds structure. It turns quantum uncertainty into the initial pattern for everything that later collapses gravitationally. This is the twist that makes inflation more than a patch. It becomes a generator of the universe's fine texture. The same mechanism that erases memory of earlier messiness also creates the first meaningful irregularities. During inflation, quantum fields cannot sit perfectly still, even in their ground state. The inflaton and metric fluctuations exhibit quantum fluctuations with a calculable spectrum, set by the expansion rate and the shape of the potential. In ordinary settings, these fluctuations remain microscopic, jittering around and averaging out. But inflation stretches wavelengths enormously, taking what began as subatomic ripples and promoting them to cosmic scales. It is as if the universe takes a quantum whisper and amplifies it into a map. A fluctuation that begins smaller than an atom can be pulled to astronomical size. As a mode's wavelength stretches beyond the horizon scale during inflation, its oscillation effectively freezes. Freezes here means the mode stops behaving like a wave that sloshes back and forth, and instead becomes a fixed offset in the field value. Later, when the horizon grows and the mode re-enters, that offset shows up as a real density difference. The perturbation becomes a classical-looking imprint, even though its origin was quantum. This is the bridge from Chapter 2's restless vacuum to the cosmic web we map today. The vacuum's statistical texture becomes the universe's initial conditions, and those conditions later guide gravitational collapse. The nothing of quantum fields becomes the something of galaxies, clusters, and voids. When we look at deep surveys, we see filaments and walls spanning hundreds of millions of light-years. Inflation suggests those structures began as tiny variations in an almost uniform early state. The imprint is visible first in the CMB. Tiny temperature anisotropies trace tiny density variations at recombination, and they appear as a mottled pattern across the sky. The pattern is not random noise, but a structured randomness with a specific spectrum. Those variations match inflation's prediction of a nearly scale-invariant spectrum, meaning similar power across a wide range of scales. Nearly matters, because the slight tilt carries information about the inflaton's dynamics. Observations sharpen this into numbers. The spectral index is close to, but not exactly, 1, consistent with slow-roll inflation, where the potential is nearly flat, but not perfectly. That small deviation is a clue that the inflaton energy was changing gradually during inflation. The fluctuations are also close to Gaussian, meaning they resemble a random field whose statistics are mostly captured by the two-point correlation function. In plain language, the CMB looks like a simple kind of randomness, not a heavily skewed or spiky one. Near Gaussianity is not a trivial detail, it is a fingerprint of simple inflationary dynamics. Many alternatives produce stronger non-Gaussian signatures, which would show up as distinctive correlations among hot and cold spots. Current measurements from satellites and surveys keep inflation in the lead, though not uniquely. The data do not prove a single model, but they do fence in what the early universe could have been. Each constraint is like tightening a net around the space of possibilities. Inflation also predicts a specific relationship between density perturbations and gravitational waves, depending on the model. Primordial tensor modes would leave a B-mode polarization pattern in the CMB, a faint swirling signature in the polarization field. Detecting that pattern would be like hearing the universe's earliest tremor, a direct imprint of space-time ripples. The search continues, and the absence so far narrows the model space. Some models predict tensors too small to see, while others have already been pushed into tension. Even without a detected tensor signal, the scalar perturbations fit remarkably well. The acoustic peaks in the CMB power spectrum trace oscillations in the early plasma, where gravity pulled matter inward and radiation pressure pushed outward. These oscillations are like sound waves in a hot, dense medium, frozen into the CMB at recombination. Inflation supplies the initial phase coherence that makes those peaks sharp and predictable. Without a coherent start, the peaks would smear, and the spectrum would look less like a clean fingerprint. At this point, inflation looks like a solution that is both elegant and testable. Yet it is still an early universe hypothesis with moving parts, and the parts matter. It requires a field, a potential, and initial conditions that place the field in the right regime. The potential must be shaped so the field rolls slowly enough to sustain acceleration, yet not so slowly that inflation never ends. The theory's strength is that it connects geometry, microphysics, and observation, but that connection also exposes where our ignorance lives. That last requirement reopens the central question in a new form. If inflation explains why the universe looks smooth and flat, what explains why inflation started? If the inflaton began in a special state, are we simply relocating, fine-tuning to an earlier layer? The question is not hostile, it is diagnostic. It asks whether inflation is a final explanation or a powerful intermediate step. In a story about beginnings, an intermediate step can still be transformative, but it cannot be the last word. Inflation also must end, or it would erase the hot Big Bang we actually infer. Ending inflation means the vacuum-like energy must convert into ordinary particles and radiation. That conversion is called reheating, and it is the handoff to the familiar thermal history. In many models, reheating is not instantaneous, and the details can affect particle abundances and even dark matter scenarios. But at the narrative level, reheating is the moment the universe becomes hot in the ordinary sense. Reheating is not a decorative epilogue, it is the mechanism that makes a hot universe. As the inflaton rolls down its potential or decays, its energy is transferred to other fields through couplings, producing particles in enormous numbers. The process can involve oscillations of the inflaton around a minimum, and in some cases explosive particle production called preheating. Particle production fills space with a hot plasma, resetting the cosmic clock in temperature. The visuals can shift from a smooth, dark expansion to a sudden bloom of radiation, like embers igniting across an expanding canvas. After reheating, the standard Big Bang picture takes over with new initial conditions. The universe is hot, dense, and expanding, with perturbations already imprinted as slight over and under densities. Nucleosynthesis, recombination, and structure formation proceed as in the textbook story, but with inflation's preface. The hot Big Bang is no longer the absolute beginning, but a phase that begins after a different kind of beginning. It is the moment the universe becomes a thermal system we know how to calculate. So inflation is often described as what happened before the hot Big Bang. It is a phase that sets the stage, then exits, leaving behind a universe that looks as if it started smooth and nearly flat. But the phrase before remains dangerous, because inflation itself may not be the first chapter. In cosmology, before can be a coordinate habit rather than a physical fact. We use it because our language leans on time, even when time may be emerging. Now the tone darkens, because many inflation models do not end cleanly everywhere. Quantum fluctuations do not only seed density perturbations, they can also kick the inflaton field upward in parts of space. In those regions, the field climbs to higher potential energy, and inflation continues longer. While one region reheats and becomes hot, another region keeps inflating, becoming smoother and emptier. The consequence is not a single graceful exit, but a patchwork of endings. This is eternal inflation, and it changes the meaning of the universe. Inflation ends locally in patches, creating reheated regions like ours, sometimes called pocket universes. But globally, the inflating background keeps expanding faster than it decays, so the total inflating volume grows without bound. Even if many regions stop inflating, the ones that continue create more volume than the ones that end. The process becomes self-sustaining. driven by the interplay of expansion and quantum chance. In that picture, our observable universe is one reheated bubble or pocket. Other pockets can form with different histories, and in some models different low-energy physics, depending on how fields settle into different vacua. The multiverse is not added for drama. It emerges from the dynamics of inflation plus quantum randomness. It is a consequence that many physicists treat cautiously, because it is both natural in the equations and difficult to test directly. The unsettling part is not the imagery, but the shift in what typical means. Bubble universes can nucleate like phase transition droplets in a supercooled medium. Each bubble has its own hot Big Bang after reheating inside it, and its own expanding space and cooling plasma. The space between bubbles continues inflating, keeping them causally separated and preventing easy observational contact. The visuals here are stark, glowing spheres forming in a dark, rapidly stretching background, each sphere a cosmos with its own internal sky. The distances between them grow so fast that even light cannot carry messages across the gaps. This is where inflation's explanatory power becomes unsettling. The same mechanism that smooths our patch also generates an unending production of patches. The theory begins to predict not one universe, but an ensemble, and the ensemble raises new questions about probability and explanation. If there are infinitely many pockets, what does it mean to say something is likely? If every allowed outcome occurs somewhere, what does it mean to predict a specific one here? If anything that can happen does happen somewhere, then prediction becomes statistical. We must define measures over infinite volumes, which is technically hard and conceptually slippery. The measure problem is not a minor detail, because it affects what inflation claims to predict. Different ways of counting regions can yield different expectations for what an observer should see. In a theory with infinities, counting becomes physics. The multiverse also pressures the boundary between physics and metaphysics. If other bubbles are forever beyond our horizon, evidence becomes indirect, filtered through what inflation predicts for our local patch. We can still test inflation's local predictions like the spectrum of perturbations and their correlations, but the global picture risks becoming underdetermined by data because it speaks about regions we cannot access. The documentary's mystery deepens here, because the mathematics seems to point beyond the observable. Even if we accept eternal inflation, the central question returns with sharper teeth. Does eternal inflation remove the need for a beginning, or does it merely postpone it? If inflation is eternal to the future, what about the past? Is the inflating background an everlasting sea, or does it have an edge that our equations cannot cross? The desire for an eternal past is understandable, yet nature may not grant it. Here we introduce a result that is often misunderstood, yet it matters for the story's spine. The border Vilenkin theorem argues that many inflating spacetimes cannot be extended infinitely into the past. If the average expansion rate along a past-directed world line is positive, that world line is past incomplete. The theorem is not a model of what came before, but a constraint on what inflation can be by itself. It tells us that inflation forever has limits when we look backward. Past incomplete does not mean a singularity must exist in the classical sense. It means the inflationary description cannot be the whole story all the way back, at least not for the broad class of spacetimes the theorem addresses. The spacetime has a boundary in the past, or at least a limit where the inflating phase stops being a valid extension. That limit could be a quantum regime, a different phase, or a breakdown of classical geometry. The theorem points to incompleteness, not to a specific origin mechanism. The accessible framing is this. Expansion acts like a one-way stretching of geodesics, and sustained stretching prevents an infinite past history for typical observers. If the universe has been expanding on average, then tracing trajectories backward hits an edge in finite proper time. Proper time is the time measured by a clock carried along a world line, and the theorem speaks in that language. It says that for many observers, you cannot keep extending the inflating history endlessly into earlier and earlier moments. The story runs out of road. This is disturbing because inflation was often sold as an escape from the initial singularity. It can smooth away many initial condition problems, and it can push the classical singularity out of view in practical calculations, but it may not erase the need for an initial boundary. Inflation can be eternal forward, yet still require something earlier than inflation. The beginning becomes less like a point in the hot Big Bang, and more like a boundary behind the inflationary curtain. So we face two unsettling options, and neither is comfortable. If inflation is not eternal, then we must explain why it began in the first place, and why it began in a state that produced enough e-folds. If inflation is eternal to the future, it may still have a past boundary, which demands a pre-inflationary phase or a deeper principle. Either way, inflation does not dissolve the origin question, it reshapes it. The question becomes, what selects the conditions that make inflation possible? One response is to propose that the boundary is not a beginning in time, but a beginning of classical space-time. The earliest description might be quantum, Euclidean, or otherwise non-classical, where time is not yet a reliable parameter. In such proposals, the familiar arrow of time emerges when the universe enters a semi-classical regime and inflation begins. Inflation would then be an emergent phase that starts when classical expansion becomes meaningful. The language shifts from what happened first to when does time become a good approximation. Another response is to look for cosmologies that avoid a past boundary by changing the early behaviour. A contracting phase followed by a bounce could replace the boundary with a transition. In that case, inflation might be preceded by contraction, or replaced by a different mechanism for generating perturbations. The motivation is consistent with our theme, to cross the apparent edge without invoking a first moment. Yet the alternative must still do the same observational work that inflation does so well. But bounces come with their own costs. Contraction can amplify anisotropies and inhomogeneities, making a smooth bounce difficult without special matter or modified gravity. Small departures from uniformity can grow rapidly, and shear can dominate, threatening to shred the would-be smooth universe. Any alternative must still reproduce the observed perturbation spectrum, near Gaussianity, and the CMB's acoustic structure. The bar is high because the data are precise, and the early universe left a detailed record. So inflation remains the best developed bridge from quantum vacuum structure to the observed universe. It explains why the sky is uniform, why space is nearly flat, and why structure begins as a specific pattern of fluctuations. Yet it also points beyond itself toward questions it cannot settle. It is a theory that works almost too well, and that success makes its remaining gaps more visible. The more clearly it explains the middle, the more sharply it outlines the unknown at the start. Inflation makes the beginning feel less like a point and more like a process. The universe can start by expanding, with geometry doing the work of making a common past. But the mechanism that makes a beginning look natural also multiplies beginnings elsewhere. If inflation is generative and stochastic, then our beginning may be one of many, selected by chance and constrained by physics. That thought is both exhilarating and disquieting, because it changes what our story means. This is where the documentary's central question tightens again. Did anything exist before the Big Bang, or is before the wrong category for the earliest regime? Inflation suggests a prior state that is not empty, not static, and perhaps not even unique. It suggests that what we call the Big Bang is a reheating event inside a larger inflationary context. Yet it also suggests that inflation itself may be a chapter that begins at a boundary we cannot yet describe. If the inflaton is an effective field, then it presupposes deeper degrees of freedom. If the false vacuum is metastable, it presupposes a landscape of possible vacua, even if we do not yet know how to derive that landscape from first principles. If quantum fluctuations seed everything, they presuppose quantum rules that already operate before the hot universe appears. Each presupposition is a clue that our current description is layered. The question becomes whether the deepest layer is accessible to science or only to speculation. The unsettling implication is that inflation can explain almost everything we see, while leaving the deepest why untouched. It can replace fine-tuning with dynamics, then reintroduce fine-tuning as a question about the inflaton potential and initial conditions. It can replace a singularity with a boundary, then force us to ask what the boundary means. And it can produce a multiverse naturally, then confront us with the problem of extracting definite predictions. The theory's power and its unease arrive together. We end this chapter with a controlled pivot, not a conclusion. Inflation is the first whisper of time in the sense that it gives the universe a direction and a memory, setting initial conditions that persist for billions of years. Yet the whisper comes from a throat we cannot see, and the equations hint that something lies on the other side. The camera lingers on the CMB sky, then fades into darkness where the map no longer reaches. In that darkness, the boundary waits, mathematical, physical, and philosophical. If inflation cannot fully explain the beginning, we must ask whether the universe had a prior phase. The next chapter follows that possibility into bounces, cycles, and attempts to cross the boundary without invoking a first moment. We will keep the same discipline as before, using observation as a compass, even when the terrain becomes strange. The goal is not to replace one mystery with another, but to see which mysteries are forced on us by the data. And in that pursuit, the first whisper of time becomes an invitation to listen harder. Inflation gave us a powerful prologue, yet it left a boundary in the past. The question returns with new force, because the mind keeps pushing behind the curtain. Did anything exist before our hot beginning, or is before still a trap? An artifact of how human language handles change. Visually, the familiar timeline appears like a bright flare at the left edge of a graph. We draw an arrow, label it time, and pretend the paper itself is neutral. Yet the moment we ask what lies to the left, beyond the flare, we discover that our drawing quietly assumed what we're trying to test. The axis already smuggled in a smooth classical notion of duration, even though the early universe may not grant us that luxury. Chapter 4 follows models that treat the Big Bang as a transition, not a first moment. The shared move is simple, but the implications are unsettling. Replace the classical singularity with new physics near the Planck scale, where gravity and quantum theory can no longer ignore each other. In that regime, the initial condition problem becomes a regime change problem, and the boundary becomes something we might cross. In general relativity, running the clock backward drives density and curvature toward infinity. That infinity is not a place we can trust, because our equations are being asked to operate outside their jurisdiction. In practice, it is a warning light that says, you're missing degrees of freedom. It's the same kind of warning that appears when fluid equations fail at molecular scales, because the missing atoms finally matter. A singularity is often described as a point, but that language can mislead. In the mathematics of space-time, it is better understood as geodesic incompleteness, paths that simply end, even when no physical obstacle is specified. The theory stops giving instructions for what happens next, and the universe becomes a question mark. Even light rays and freely falling observers can reach an edge in finite proper time, as if the map had been torn. The Planck scale is where this breakdown becomes unavoidable. At roughly 10^35 meters and around 1019 giga, electron volts quantum fluctuations of geometry itself should become violent. The Planck time, about 10^43 seconds, marks a regime where earlier may not behave like ordinary earlier. If space-time is not a fixed stage, then the idea of a smooth temporal parameter may be only an approximation, like a coastline that looks continuous until you zoom in. A bounce is the claim that the breakdown becomes a turning point. Instead of the scale factor shrinking to zero, it reaches a minimum and rebounds. The Big Bang then becomes a phase change in the cosmic story. Dramatic, luminous, but not necessarily the first page. It is less a creation event than a conversion event, where the universe changes how it stores energy and geometry. The big bounce idea starts with a limit. When density approaches Planck values, space-time may resist further compression, not by adding a conventional force, but by changing what gravity means. Quantum geometry, quantum pressure, or new degrees of freedom can generate an effective repulsion. In many proposals, the repulsion is not a separate ingredient placed on top of Einstein's equations, but a correction that emerges when the underlying microstructure is treated honestly. The repulsion is not a force added by hand in ordinary space. It is a change in the gravitational response when the microscopic structure of space-time becomes discrete or strongly quantum. Contraction slows, halts, then reverses into expansion. The mathematics often looks like a sign change in an effective term, but the physical claim is deeper. Gravity itself becomes less like an attractor and more like a regulator. To picture it, imagine a film of a collapsing universe played in reverse. Galaxies fade into a hot mist, then into a nearly featureless plasma, and then into a state where distance itself becomes ambiguous. At the bounce, the camera passes through a frame we cannot fully render, then the film resumes as expansion. The soundtrack, if we could hear it, would rise from a low cosmic hum into a sharp, broadband hiss as quantum fluctuations crowd the stage. This reframes the Big Bang. Our beginning becomes the moment after the turnaround, when the universe is hot and rapidly expanding. The earlier chapter is a contracting cosmos whose details are mostly erased, like chalk marks washed by a sudden rain. Yet the erasure is selective, because the universe still has to remember enough to produce the precise pattern of temperature and polarization we measure today. But erasure is never free. A bounce must preserve enough information to match what we observe, while hiding the chaos that contraction can amplify. The model must also avoid pathologies like ghosts, instabilities, or violations of basic consistency. In other words, it must be both dramatic and disciplined, because the equations will punish any hidden inconsistency. There is a technical reason contraction is dangerous. In many contracting solutions, anisotropies grow faster than ordinary matter, and shear terms can dominate the energy budget. If that happens, the universe does not bounce into something smooth. It collapses into a chaotic, mix-master-like state. The Bianchi models that illustrate this behavior are not just mathematical curiosities. They are reminders that generic contraction can turn orderly geometry into a tumbling anisotropic storm. So the bounce is not merely a poetic reversal. It is a dynamical claim about equations that must remain stable under perturbations, and about quantum corrections that must not explode. The closer we get to the Planck regime, the more unforgiving the bookkeeping becomes. Tiny errors in assumptions can become enormous errors in outcomes, because the system is operating at the edge of its own description. One of the best-known frameworks is loop quantum cosmology. It is a symmetry-reduced application of loop quantum gravity ideas to homogeneous universes, where the infinite complexity of full quantum geometry is compressed into a manageable set of variables. It should be treated cautiously, because the results depend on quantization choices and approximations. Still, it offers a concrete example of how a singularity can disappear without simply being wished away. Loop quantum cosmology begins with a radical claim. Space-time geometry is not continuous at arbitrarily small scales, even if it looks smooth to us. Areas and volumes come in discrete chunks, and that discreteness changes the Friedmann equations at high density. The analogy is imperfect, but helpful. A smooth fabric can look continuous from afar, while revealing a weave when you bring it close to your eye. In loop-based approaches, the fundamental variables resemble connections and holonomies, more like the language of gauge theory than the language of classical metric fields. Curvature is encoded through finite loops, not infinitesimal ones, and that subtle change matters when the loops cannot be shrunk further. The continuum becomes an approximation, not a birthright. When the smallest loop has a non-zero area, the usual divergence of curvature can be tamed, because infinite curvature would require loops smaller than the theory allows. In the effective description, the classical term that drives collapse is modified. As density rises, a correction term grows and can flip the sign of the effective gravitational pull. The scale factor reaches a minimum, then increases. The bounce appears as a robust feature in many simplified calculations, but the documentary must keep its caution visible. Robust in a model is not the same as inevitable in nature. A common way to express this is through a modified Friedmann equation. Instead of h(2) being simply proportional to density, it becomes proportional to density times a factor like 1 rRc. When R approaches the critical density Rc, the expansion rate goes to 0, then changes sign. The equation is compact, yet it carries an entire worldview. The universe has a maximum effective density, and the singularity is replaced by a regulated peak. The bounce density is typically of order the Planck density, not an adjustable everyday parameter. Below that regime, the equations reduce to standard cosmology, so the familiar successes are retained. Above it, the classical singularity is replaced by a quantum bridge. The bridge is not a tunnel through space, but a continuation of evolution through a region where classical geometry is no longer the right language. The image is striking. The curve of the scale factor dips, touches a floor, and rises again, as if the universe had a built-in safety rail. Yet the safety rail is not visible in ordinary conditions, because it only appears when density becomes almost unimaginably large. In a visual sequence, the graph could be overlaid on a star field that compresses into a bright, granular fog, then relaxes into the familiar expanding cosmos. This sounds like a clean rescue, yet the documentary tension sharpens here. The bounce is derived in a simplified setting with strong symmetry assumptions, where the universe is taken to be homogeneous and often isotropic. Real universes have anisotropies, inhomogeneities, and quantum states that may not cooperate, Even small deviations can matter, because contraction tends to amplify what expansion would dilute. Researchers test whether the bounce survives when the universe is less idealized. They study anisotropic models, perturbations, and different matter contents, because matter can couple to geometry in ways that amplify trouble. The outcome is mixed and model-dependent, which keeps the claim provisional. Some settings preserve a bounce but distort the perturbations, while others threaten stability unless additional conditions are imposed. Even within loop quantum cosmology, there are choices that matter. Different prescriptions for quantization can shift details of the effective dynamics, and different assumptions about the quantum state can change how sharply the bounce occurs. The broad picture can remain, while the fine print becomes decisive. This is not a weakness unique to loop ideas. It is a common feature of quantum gravity, where multiple routes can approximate the same classical limit. Another subtlety is the fate of cosmological perturbations. The universe we observe is not perfectly smooth, and the seeds of structure must pass through whatever replaces the singularity. If the bounce scrambles phases or amplifies certain modes, it could leave fingerprints, or it could ruin the match to the CMB. The perturbations are not decorative details, they are the forensic evidence that any early universe story must explain. Even if a bounce occurs, another question appears. What carries the arrow of time through the bounce, and what sets the initial conditions on the contracting side? A bounce can move the boundary, yet it can still hide a deeper boundary. If the bounce is a bridge, we still have to ask what determines the traffic rules on each side. The arrow of time is not just a philosophical flourish. In physics, it is tied to entropy, to coarse graining, and to why we remember the past but not the future. If a contracting universe becomes more ordered as it approaches a bounce, what does that imply about the direction in which time points? The question is sharp because our everyday arrow is thermodynamic, not geometric, and a bounce forces the two to negotiate. Some bounce narratives suggest that time continues smoothly through the minimum, with entropy increasing on both sides in opposite directions. Others treat the bounce as a moment where our usual thermodynamic intuitions fail. Either way, the bounce forces us to specify what we mean by earlier, not merely to reuse the word. The audience should feel the conceptual strain here, because the model is asking language itself to stretch. A second family of models aims to make contraction itself do the smoothing. These are ekpyrotic and cyclic scenarios, often motivated by ideas from higher dimensional theories. They propose a slow, ultra-stiff contraction before the bounce, a phase that can last far longer than the brief flash of the hot Big Bang. The length of that phase is part of the appeal, because it offers time for the universe to become orderly, without invoking an exponential expansion. The word ekpyrotic comes from ancient Stoic imagery of a cosmic conflagration, a universe periodically reborn through fire. Modern ekpyrosis is not mythology, but the name retains that sense of renewal under pressure. The key is the equation of state, a relationship between pressure and energy density. In plain terms, it tells you how hard a component pushes back when you try to compress it. Ekpyrotic contraction uses an equation of state with very large pressure compared to energy density. That stiff behavior suppresses curvature and anisotropy relative to the dominant component. The universe becomes flatter and more homogeneous as it contracts. In the visuals, the messy, lopsided collapse that relativity would normally permit is replaced by a controlled narrowing, like a lens focusing light rather than shattering it. In technical terms, the energy density of an ultra-stiff component grows faster, with decreasing scale factor, than the energy in anisotropic shear. As the cosmos shrinks, the stiff field overwhelms the terms that would otherwise produce chaotic collapse. The contraction becomes a kind of dynamical filter. The universe is not guaranteed to be smooth, but the equations can make smoothness an attractor, which is exactly the kind of behavior a pre-Big Bang phase needs. This is the mirror of inflation's achievement, but achieved with opposite kinematics. Inflation smooths by rapid expansion that dilutes gradients and stretches quantum fluctuations across cosmic distances. Ekpyrosis smooths by slow contraction that dynamically dominates over shear and curvature. The symmetry is almost poetic, yet the physics is not symmetrical, because perturbations behave differently when the universe is shrinking. The mechanism is attractive because it addresses the same forensic clues. It targets the horizon-like uniformity and near flatness without requiring an inflating vacuum. It also promises a prehistory that is long and classically describable, an extended runway before the bounce. That runway is where intuition can breathe, because the model is not forced to begin in an unknowable instant. That runway matters for intuition. Inflation asks us to accept that a tiny patch expanded exponentially, and that our visible universe is a magnified remnant of that patch. Ekpyrosis asks us to accept the opposite. A vast region slowly compressed, while becoming simpler rather than messier. The unsettling twist is that contraction, which seems like it should amplify disorder, can under certain conditions act like a cosmic straightener. Yet ekpyrotic models face their own technical cliffs. Generating the observed nearly scale-invariant spectrum is not automatic, because contraction tends to produce a blue-tilted spectrum for simple curvature perturbations. Many versions require multiple fields, carefully shaped potentials, and controlled conversion from entropy to curvature perturbations. The story remains economical in concept, but it becomes intricate in execution. This conversion is delicate. One field can carry the background evolution, while another carries isocurvature fluctuations that later become curvature fluctuations. The timing of that handoff, and the shape of the potential during it, can determine whether the model matches the CMB or fails decisively. In animation, we could show two coupled waves, one hidden and one visible, exchanging energy as the bounce approaches. The predicted non-Gaussianity can be larger than in simple inflation. That becomes a lever for observational tests, but also a risk, because non-Gaussian patterns are constrained by precise measurements. Data from the CMB strongly limits certain shapes and amplitudes, narrowing the viable parameter space. The model is therefore testable in principle, but only if the signatures survive the messy details of the bounce. Non-Gaussianity is more than an abstract statistic. It is a measure of whether the primordial fluctuations were simple, nearly free quantum fields, or whether they interacted strongly in the early universe. A large bispectrum would be a signature of drama, of fields talking to each other in the primordial dark. The question for the viewer is almost cinematic. Was the early universe a quiet solo, or a crowded conversation? Cyclic versions extend the story further. The universe repeats through phases of expansion, dilution, contraction, and bounce. Each cycle is an aeon, and our Big Bang becomes the latest rebound. The repetition offers a kind of cosmic continuity, yet it also forces the theory to pay every bill that accumulates over time. The narrative appeal is obvious. A cyclic cosmos avoids a unique beginning by replacing it with recurrence, like a heartbeat rather than a birth. The disturbing possibility is also obvious. If cycles extend far into the past, the universe may be ancient beyond comprehension. The camera could pull back to show nested rings of cosmic history, each ring a full universe, fading into darkness. When we imagine such a cosmos, the visuals change. Instead of a single explosion, we see a sequence of cosmic eras, galaxies forming, fading and reforming, like waves rolling onto a shore. The question becomes not what started it, but what keeps it going. What is the engine that makes the rhythm stable, rather than a one-time coincidence? But cyclicity collides with a brutal accounting rule. Entropy tends to increase, and increased entropy accumulates from cycle to cycle. Without a reset, later cycles become larger, messier, and less like the clean early universe we infer. The second law is not a suggestion, and it does not soften just because the story is elegant. This is the entropy problem for cyclic universes. In a closed system, disorder grows, and a truly periodic return becomes impossible. A cyclic model must explain how each cycle avoids inheriting an ever-growing burden. It must also explain why the arrow of time does not simply point in one direction across all cycles, turning cyclic into a misleading label. The burden is not just heat. It includes black holes, relic particles, and the irreversible record of processes that have already happened. Even if the universe contracts again, those records do not politely vanish, and the next cycle begins with extra baggage. The viewer should picture a universe trying to restart while carrying the ash of its previous fires. Several workarounds exist, each with costs. Some proposals rely on vast expansion phases that dilute entropy per comoving volume, so that any given region looks clean again. Others invoke new degrees of freedom that carry entropy away, or mechanisms that effectively discard regions. The fixes differ in style, but they share a theme. Entropy must be managed, not ignored. Dilution sounds simple, but it hides a geometric trick. If the universe expands by an enormous factor, the entropy density can become tiny, even if the total entropy is huge. The model then depends on what we mean by the same universe, from cycle to cycle, global total or local patch. That distinction is not wordplay. It determines whether the model is cyclic in substance or only in appearance. There are also conformal ideas that try to make late-time emptiness look like a new beginning. If the universe becomes dominated by radiation-like or massless behavior, scales can lose meaning. Then a cold, empty future can be mapped to a hot, dense past. The conceptual move is subtle, because it suggests that what matters is not size but shape, angles and causal structure rather than rulers. The visual metaphor is elegant. In the far future, matter thins out, wavelengths stretch, and the cosmos becomes a near-perfect vacuum with rare photons. If all that remains is effectively massless, then the universe has no preferred rulers, only angles and light cones, the geometry of causality. The screen could fade from a crowded galaxy field to a nearly black frame, punctuated by a few drifting points of light. These conformal cyclic approaches shift the problem. They must explain how massive particles fade from relevance and how black holes and their entropy are handled. They also must reproduce the precise perturbation statistics seen in the CMB. The theory can be graceful in its mapping, yet unforgiving in its required details. Black holes are especially stubborn. They store enormous entropy in their horizons, and they do not disappear quickly, except through Hawking radiation over vast timescales. A cyclic picture must decide whether black holes evaporate away cleanly, or whether their information and entropy poison the next aeon. Even the evaporation story raises deep questions, because it ties cosmic history to quantum information, not just to thermodynamics. Every cyclic fix raises a new question about what is being assumed. Is entropy truly removed, or merely moved out of the region we track? Is the cycle global, or is it an effective cycle within a larger multi-region spacetime? The viewer is invited to notice a pattern. Solving one boundary problem often introduces a boundary of another kind. That distinction matters because it changes what counts as an explanation. If the universe is cyclic only in a selected patch, we must ask what selects the patch. If the universe is cyclic everywhere, we must ask how global consistency is enforced across bounces. The camera can linger on a mosaic of regions, some cycling, some not, to make the conceptual tension visible. Now the story widens into higher dimensions. Some bounce and cyclic ideas are inspired by string theory and brain-world pictures. In these models, our observable universe is a three-dimensional brain embedded in a higher dimensional bulk. Historically, these ideas grew from attempts to unify forces and include gravity consistently, and cosmology became a testing ground for their most dramatic implications. The brain is not imagined as a sheet floating in ordinary space. It is a dynamical object in a higher dimensional geometry, where fields and forces can be confined to the brain while gravity leaks into the bulk. The extra dimension is not elsewhere in the everyday sense. It is a new direction in the theory's configuration. In a visual pullback, the familiar star field becomes a glowing surface, with faint gravitational ripples extending into a shadowy surrounding volume. The Big Bang can be reinterpreted as a brain collision. Two brains approach, collide, and the collision energy reheats the brain into a hot expanding state. What we call before is motion in the extra dimension, not earlier time in our brain. The origin event becomes less like a first tick of a clock, and more like an impact that changes the state of a system. This changes the meaning of origin language. The place the universe began in is not a pre-existing three-dimensional room. It is a higher dimensional configuration space where separation and collision define the event. The viewer is asked to imagine that what feels like time in our world might be a projection of motion in a larger arena. In visual terms, the camera pulls back. Our entire cosmos becomes a glowing membrane, and the Big Bang becomes a flash at the moment two membranes touch. The heat is localized on the brain, while the bulk can remain comparatively quiet. An eerie contrast between violence and silence. The collision could be shown as a brief blinding line of light spreading across the brain, like lightning racing along a surface. Ekpyrotic scenarios often use this collision picture as a physical motivation. The slow contraction corresponds to brains approaching in a controlled way, smoothing the geometry. The bounce corresponds to the collision and subsequent separation. The metaphor is powerful, but the mathematics must still answer the same hard question: how to pass through the high-energy event without losing predictability. But the same tension returns in a new costume. Collisions can excite dangerous instabilities, produce singular behaviour in the bulk, or require fine-tuned potentials to avoid catastrophic outcomes. The extra dimensions add freedom, yet they also add failure modes. What looks like an elegant geometric story can become a delicate balancing act in the underlying effective theory. A collision is not automatically a gentle bounce. At high energies, brains can produce excitations that behave like unwanted relics, or they can create regions where effective field theory breaks down. The mathematics can become as sharp and unforgiving as the singularity it hoped to avoid. The viewer should feel that more dimensions does not mean fewer problems, because complexity can be both a tool and a trap. Testability becomes the central pressure point. A model that replaces the singularity must still leave traces we can search for. Otherwise, it risks becoming a story that can fit any outcome after the fact. The documentary's tone should tighten here, because the difference between physics and myth is not beauty, but vulnerability to evidence. The cleanest observational hooks come from primordial gravitational waves. Inflation often predicts a tensor background whose amplitude relates to the energy scale, and that background imprints a distinctive B-mode polarization pattern in the CMB. Many ekpyrotic models predict a much smaller tensor signal, shifting the target for experiments. A null result is not automatically a victory for contraction, but it changes which stories remain plausible. A bounce can also imprint features. The power spectrum can show oscillations, a cutoff at large scales, or specific running with scale. These effects depend on how perturbations pass through contraction, bounce, and reheating. Even small departures from a simple power law can matter, because the CMB has become a high-precision map of primordial statistics. In a contracting phase, modes can exit and re-enter horizons differently than in inflation. The matching conditions across the bounce, how one set of perturbation variables connects to another, can create phase shifts or amplitude changes. Those changes might appear as gentle ripples in the CMB spectrum, or as a suppression of power on the larger scales. The visual could overlay a smooth theoretical curve with a subtly wiggled alternative, inviting the viewer to look for the difference. Non-Gaussianity is another discriminator. Multi-field ekpyrotic models can generate distinctive bispectrum shapes, sometimes of the local type, sometimes more exotic depending on the conversion mechanism. Inflation can also generate non-Gaussianity, but simple single-field slow roll predicts it to be small. The observational question becomes a kind of fingerprint analysis, where the universe's earliest interactions leave patterns in the statistics of the sky. The CMB is the main arena for these tests, yet it is a limited arena. Cosmic variance hides the largest scales, and foregrounds complicate polarization. Many claimed anomalies are statistically fragile, and interpretations remain contested. The viewer should be reminded that the data are exquisite, but the universe gives us only one realization of them. Cosmic variance is a sobering concept. We have only one sky, and the largest angular scales provide only a few independent modes. When a model predicts a subtle feature at low multipoles, we cannot rerun the universe to check, so the evidence is always partly hostage to chance. That limitation is not a failure of instruments, but a consequence of living inside the system we are measuring. Some analyses point to low multipole anomalies, hemispherical asymmetry, or unusual alignments. Bounce models can be tuned to produce large-scale suppression or features. The danger is that tuning can mimic explanation without adding predictive power. The viewer is invited to ask a hard question. Are we seeing a message from the early universe, or a pattern our brains are eager to promote? A tuned model can always chase the data, but science demands the reverse. We want a small set of principles that implies a narrow set of outcomes, so that observation can truly threaten the idea. The more knobs a bounce model introduces, the more it risks becoming unkillable. The documentary should linger on that word, unkillable, because it is the opposite of what a scientific hypothesis should be. Gravitational wave detectors offer a second arena, but the path is hard. Space-based interferometers and pulsar timing arrays probe different frequency bands, and each band corresponds to a different slice of early universe history. A primordial background could be confused with astrophysical sources, demanding careful separation. The signal, if it exists, will arrive mixed with the universe's later noise, and the analysis must unmix them without bias. Even if a stochastic background is detected, interpretation will be a battle of populations. Merging black holes, cosmic strings, and phase transitions can all contribute. A bounce or cyclic signature would need a spectrum and correlation pattern distinctive enough to survive that crowd. The viewer should sense that detection is only the beginning, because the real drama is attribution. Large-scale structure adds constraints on primordial statistics. Galaxy surveys test the power spectrum, scale dependence, and non-Gaussian bias, because primordial non-Gaussianity changes how galaxies trace the underlying matter. These data increasingly fence in early universe alternatives, though degeneracies remain. The cosmic web becomes another screen on which the early universe might have left a faint watermark. Across all these models, the same trade appears. Removing the singularity often requires exotic ingredients, modified gravity, or quantum corrections that are difficult to derive uniquely. Each ingredient can solve one problem while creating another. The viewer should feel the weight of that trade because it is the honest cost of pushing physics into a regime where our best-tested theories overlap and clash. Bounces must be stable against anisotropy growth during contraction. Cycles must confront entropy accumulation and the thermodynamic arrow. Brainworld collisions must avoid uncontrolled singularities and must connect to a consistent high-energy theory. Each line sounds simple, yet each hides years of technical work and a forest of assumptions. Even the word bounce hides multiple mechanisms. Some rely on quantum geometry effects, like in loop quantum cosmology, where discreteness modifies the high-density dynamics. Others rely on matter that violates the usual energy conditions, such as ghost condensates or Galilean-like fields. The documentary should keep the viewer oriented here, because different mechanisms imply different risks and different observational consequences. Energy condition violation is not automatically forbidden, but it is dangerous. It can imply negative kinetic energy, runaway instabilities, or superluminal propagation in effective theories. Model builders try to thread a narrow needle between possibility and pathology. The needle is narrow because the same trick that prevents a singularity can also destabilize the vacuum. If fluctuations can borrow unlimited negative energy, the theory can decay catastrophically. So the bounce must be engineered so that the effective description remains controlled, at least long enough to pass through the turnaround. This is where the narration can briefly slow, letting the viewer feel the precariousness of building a bridge over an abyss. The documentary's mood turns more mysterious here. Each proposal tries to cross the boundary that inflation could not cross, and each proposal pays for that crossing with new assumptions. Each proposal implies that our Big Bang might be a memory wipe, not an origin. If the universe has a prehistory, then the absence of direct evidence becomes part of the story, not just a missing scene. If a prior universe contracted, what was it like? Was it similar to ours, with galaxies and black holes? Or was it a sparse cold phase dominated by fields? Different models answer differently, and the answers affect what can pass through the bounce. In visuals, we might glimpse ghostly silhouettes of earlier galaxies, then watch them dissolve into a smooth, featureless field as the contraction tightens. Some scenarios suggest a long, dilute prehistory, where structure is washed away. Others allow a complex previous cosmos whose information is mostly scrambled at the bounce. The disturbing possibility is that evidence of before may be fundamentally unreadable, not because we lack cleverness, but because the mapping between phases may erase the very variables that would carry a clear record. That unreadability is not only practical, it may be principled. If the bounce occurs at Planck densities, semi-classical notions of space-time may fail, and our usual observables may not be well defined. The very variables needed to describe before may not map cleanly onto the variables we measure after. The viewer should feel the ground shift here because the question is no longer what happened, but what can be meaningfully asked. This is where the visuals should slow down. The screen fills with quantum foam imagery, flickering geometry, transient horizons, and a sense that the stage itself is unstable. The narrator's words become careful because the subject is no longer a place, but a regime where place is questionable. A subtle sound design could emphasize discontinuity, like a signal breaking up as it approaches the bounce. Yet scientists keep pushing because the singularity is an admission of incompleteness. A bounce is a demand that physics remain lawful at the edge, even if the laws change their form. The cost is that the edge may be governed by rules we cannot yet derive or test. That tension between the desire for completion and the limits of access is the emotional core of this chapter. There is also a historical echo here. Singularities were once treated as curiosities, but the singularity theorems of Penrose and Hawking made them hard to dismiss within classical relativity. Those theorems do not prove that nature contains infinities, but they do prove that classical spacetime cannot be the whole story. They show that under broad conditions, gravity focuses geodesics until the classical description runs out, which is exactly why quantum gravity is not optional. We can summarize the competing strategies in one line. Inflation smooths by expansion, ekparosis smooths by contraction, and bounces attempt to connect the two without infinities. Cycles attempt to repeat the connection indefinitely. The summary is neat, but the reality is jagged, because each approach must satisfy both mathematical consistency and observational restraint. But summarizing is not the same as understanding. Each strategy has a different relationship to initial conditions, to entropy, and to what counts as generic behavior. The deeper question is whether any of them truly removes the beginning, or merely relocates it. If the boundary moves, does it become less real or only less visible? Now we return to the central question with sharper language. If the Big Bang is a transition, then something existed before in some form. It could be a contracting spacetime, a higher dimensional configuration, or a quantum gravitational phase. The models differ, but they agree on one provocation. The hot beginning might be a middle. Yet even that sentence hides a choice. We are using the grammar of time, before and after, while discussing models that may redefine time near the Planck regime. Perhaps before is not a coordinate, but a relationship between phases of a deeper system. If so, then the universe's refusal to begin is not a loophole in chronology, but a clue about what chronology really is. But the deeper question remains untouched. What is the stage on which any bounce or cycle occurs? If spacetime itself is emergent, then a previous universe may be a different phase of a deeper structure, not a prior chapter in the same book. The viewer should feel the approach of the next chapter here, because the story is about to shift from events in spacetime to the possibility that spacetime is not fundamental. This is the transition we need for the next chapter. Bounces and cycles suggest a prehistory, yet they also force us to ask what counts as a boundary. If the universe refuses to begin, we must ask what it means to exist at all. The question is no longer only cosmological, it becomes structural, about the rules that make any cosmos possible. The next step is to interrogate the stage itself. We follow ideas where time and space are not fundamental, and where before becomes a relationship inside a timeless framework. The disturbing hint is that the truest origin may be rules, not events. We keep asking what existed before the Big Bang, and the question keeps changing shape as our theories sharpen. Chapter 3 gave inflation as a prologue, and Chapter 4 offered bounces and cycles, each one stretching the meaning of beginning. Now we widen the frame again, toward proposals where our cosmos is not the whole. The disturbing implication is not only more space, but less certainty about what counts as an explanation. Visually, this chapter begins with a familiar image. Galaxies scattered like embers across a black field, then it quietly pulls back. The Milky Way becomes a pinprick, the local group a faint smudge, and the cosmic web turns into a lacework of filaments. As the camera retreats, filaments thin into a gauzy mesh, and clusters become mere knots in a vast pattern. The camera keeps retreating until even that web looks like a texture on the surface of an expanding sphere. At that scale, outside stops feeling like a direction, and starts feeling like a conceptual trap. First, we define terms, because the argument collapses without clean language and careful boundaries. The observable universe is the region we can see, limited by light travel time and cosmic expansion since the hot early era. It is not a physical bubble wall, and it is not a border where matter ends. It is simply the portion of space-time that has had time to send us information. In practice, it is set by our past light cone, an ever-growing record of what could have reached us since the early fireball. The observable radius is often quoted as about 46 billion light-years, even though the universe is about 13.8 billion years old. That mismatch is not a mistake, and it is not a paradox. Space has expanded while light was in transit, so the present-day distance to the emitting matter is larger than the light travel distance. When we look far away, we're also looking back in time, toward a younger, hotter cosmos. The farthest light we see comes from the surface of last scattering, when electrons and nuclei first formed neutral atoms and photons finally streamed freely. The universe can mean the entire connected spacetime region that shares a common physical history and a common set of dynamical laws. That definition is already more ambitious than everything we can see, because it includes regions beyond our current horizon. Those regions may be causally disconnected from us today, yet still part of one continuous spacetime. In that sense, universe is a claim about what exists, not a claim about what we can measure. It also implies something subtle. Two regions can share a past and still be unable to exchange signals now because expansion has outrun communication. A multiverse is a larger structure containing multiple regions that are effectively separate universes, often with different initial conditions or even different low-energy laws. Effectively separate is doing real work here, and it should not be taken lightly. It can mean causal separation by horizons, separation by different vacuum states, or separation by extra-dimensional geometry. The multiverse is not one idea, but a family of ideas that share a single unsettling theme. The theme is that what we call the universe may be a local domain, typical in some ways, accidental in others. This distinction matters because horizons are not walls, they are limits of access, and access is what experiments require. Beyond our horizon could be more of the same universe, still governed by the same laws and the same particle content. That is sometimes called a leveler multiverse, though it is really just cosmic geography. It is a sober possibility, and it is almost unavoidable in standard cosmology. If space is close to flat and extends far beyond what we see, then there is no special reason our patch should be the whole. To see why, imagine the early universe as a nearly uniform plasma with tiny quantum ripples. Inflation, if it happened, stretched those ripples to astronomical scales, seeding galaxies and clusters. The ripples began as fluctuations in quantum fields, and inflation amplified them into classical density contrasts we can map today. If inflation also made space vastly larger than the region we can observe, then our horizon is just a patch on a much bigger surface. The simplest reading is that there are regions like ours, far beyond our reach, where the same physics plays out with different random initial fluctuations. The visuals here can be deceptively calm, a sphere labelled observable, surrounded by a larger sphere fading into darkness. Yet the implication is sharp, because it turns our cosmic map into a local chart. The edge of the observable universe is like the horizon at sea, not the end of the ocean. The limit is in the traveller, not in the world. And if the ocean is large enough, then even rare arrangements of matter, distant duplicates, improbable histories, become not impossible, but inevitable somewhere. The next step is more radical, and it grows directly from inflation's logic rather than from philosophical appetite. If inflation is eternal in the future, reheating happens in patches rather than everywhere, because inflation does not end uniformly. Each patch becomes a pocket universe, while the background keeps inflating and producing more patches. This is the bubble universe picture, often labelled Level 2, and it changes what outside means. Outside becomes an inflating environment with its own causal structure, not a surrounding space you could ever travel through. In this story, a universe is not a single event, but a local exit from inflation, an island of hot matter forming in a sea of accelerated expansion. The Big Bang becomes a reheating surface inside one bubble, not the origin of all space-time. Before becomes ambiguous again, because the inflating background can persist while bubbles form. The question shifts from what came before our beginning to what the larger inflating structure is. It also shifts what we mean by an initial condition, because the initial state might be a metastable phase that keeps reproducing itself. To make that less abstract, picture a vast inflating region as a kind of stretching fabric, thinning and cooling as it expands. In most places it keeps stretching, driven by vacuum-like energy that behaves like a cosmological constant. In rare places, a transition happens and inflation ends, dumping energy into particles. Those places heat up, become radiation-dominated, and evolve into universes with their own internal time. The contrast is vivid. Cold, exponential expansion outside, and a sudden hot bath of particles inside, like a spark igniting a new thermodynamic arrow. Bubble formation is described by vacuum decay in quantum field theory, and the language is precise for a reason. A false vacuum is a metastable state with higher energy than a true vacuum, like a ball resting in a shallow dip rather than the deepest valley. Classically, it could sit there indefinitely, because there is an energy barrier in the way. Quantum mechanics, however, allows tunneling through barriers that classical motion cannot cross. The decay rate depends exponentially on the action of the bounce solution, which is why tiny changes in the potential can mean enormous changes in lifetime. In field theory, tunneling is not a particle slipping through a wall, but a field configuration changing in a way that is exponentially suppressed. The calculation often uses an instanton or bounce solution in Euclideanized spacetime, which captures the least unlikely path. When a bubble nucleates, it is not born large, and it is not born slowly. It appears with a critical size set by the balance of volume energy and surface tension of the bubble wall. That wall is not a material shell, but a region where the field rapidly interpolates between vacua, carrying energy and stress like a moving phase boundary. The bubble wall expands, converting vacuum energy into particles and radiation inside the bubble, and the expansion quickly becomes ultra-relativistic. From the outside, the bubble approaches the speed of light, and it can carve through the false vacuum like a phase boundary. From the inside, the geometry can look like an open universe, with negative spatial curvature at early times. This is one reason curvature becomes an observational handle later in the chapter. The inside observer sees a hot beginning and expanding space, even though the larger spacetime never had a single global bang. Different vacua can lead to different low-energy physics after reheating, and this is where the multiverse becomes more than geography. The vacuum determines symmetry breaking patterns, particle masses, and coupling strengths, because it sets the background values of fields. Even the effective cosmological constant can differ from bubble to bubble, changing the late-time fate of each region. The multiverse becomes a catalogue of outcomes, generated by the same underlying theory. It is the same playbook, but with different ground states, different ways the fields settle when the universe cools. It is worth pausing on what different laws can mean in practice, because it is often misunderstood. The underlying equations might be the same everywhere, yet the solutions can differ, and those solutions can look like different physics. A familiar analogy is magnetism. The microscopic laws are fixed, but the magnet can point in different directions after symmetry breaking. In cosmology, the direction is replaced by which vacuum a region lands in. What changes is not the grammar of the theory, but the values of the fields that define the effective constants we measure. This is where the word landscape enters, and it is both technical and dangerous. Technical because it refers to actual solutions, dangerous because it tempts us to stop asking why. In string theory, extra dimensions can be compactified in many ways, and those ways are not cosmetic. The shape, size, and topology of the compact space determine which fields remain light and which symmetries survive. Fluxes, branes, and geometry can stabilize different vacuum states with different constants. The details matter because they feed directly into the low-energy effective action, the simplified description that governs physics at accessible energies. The number of metastable vacua may be enormous, forming a landscape of possible low-energy worlds. Estimates vary, but the phrase 10 to the 500 became famous as a symbol of the combinatorial explosion. That number is not a measured fact, and it is not a theorem carved in stone. It is a sign that the space of consistent solutions may be so large that uniqueness becomes difficult to defend. Even if the true count is smaller, the conceptual shift remains. Consistency may allow many worlds, not just one. The landscape is not introduced to avoid data, it is introduced to solve consistency problems that appear inside the mathematics. String theory needs extra dimensions, and compactification choices are real degrees of freedom rather than optional decorations. Stabilizing moduli, the fields that describe the size and shape of the extra dimensions, often requires fluxes and non-perturbative effects. Those ingredients naturally produce many minima, each one a candidate vacuum. Without stabilization, the extra dimensions would typically drift, and the constants of nature would not remain constant long enough for any stable physics. Historically, this was not the original dream of unification, and that history matters for the tone of the debate. Early hopes for a theory of everything imagined that consistency would single out a unique vacuum, fixing all constants. Over time, as more consistent constructions were found, that uniqueness became harder to maintain. The landscape emerged not as a philosophical preference, but as a reluctant reading of what the equations seemed to allow. It also echoed an older tension in physics, between laws that feel inevitable and boundary conditions that feel contingent. Eternal inflation and the landscape reinforce each other in an unsettling way, like two ideas that lock into place. inflation supplies a mechanism to populate many vacua by repeated bubble nucleation and quantum fluctuations. The landscape supplies a menu of vacua for inflation to explore, with different minima and different barriers. Together they suggest that our laws might be local environmental facts, not universal necessities. The unsettling part is not the size of the multiverse, but the possibility that explanation becomes statistical because there is no single outcome to explain. The visual language here can shift from galaxies to abstract terrain, peaks and valleys representing vacuum energy, while a rolling field explores that terrain. Some valleys are deep and stable, others are shallow and metastable, and transitions occur like sudden drops. It is a metaphor, but it tracks a real calculation. The vacuum energy influences expansion, and expansion influences which regions dominate volume. In the background, the terrain itself can shimmer, hinting that quantum fluctuations are not mere noise, but an engine that keeps the process going. At this point, the documentary must separate mathematical motivation from testability, because the two can drift apart. The mathematics of vacuum decay and inflationary fluctuations is standard quantum field theory in curved spacetime, and it has been developed for decades. Techniques like renormalization, effective field theory, and semi-classical gravity are not speculative inventions for the multiverse. They are tools used across particle physics and cosmology. What changes is the extrapolation scale, because we are pushing those tools into regimes where direct experimental anchors are scarce. The landscape is motivated by specific constructions, but the full measure of vacua is not derived cleanly, and that gap matters. We do not have a complete, non-perturbative definition of string theory in all cosmological settings. We also do not have a rigorous census of all stable and metastable solutions, even if many examples exist. The multiverse is a consequence in many models, but consequences are not confirmations. The documentary's tone should reflect that distinction. Curiosity without surrender, and ambition without pretending the evidence is already in. Now we introduce anthropic reasoning carefully, because it is often caricatured as surrender or mysticism. Anthropic arguments do not claim the universe was designed for life, and they do not replace physics with poetry. They claim that observations are conditioned on the existence of observers, which is a plain statement about selection. If a parameter varies across universes, we should not be surprised to measure a value compatible with our existence. The controversy is not the logic of conditioning, but whether the underlying ensemble is real and whether the conditioning can be made quantitative. There is a subtle shift in logic here that deserves to be spoken aloud. In ordinary physics, we try to derive constants from deeper principles, and we treat measured values as clues. In anthropic reasoning, we also treat measured values as clues, but the clue points to a conditional distribution. The question becomes, given that observers exist, what range of values should they typically observe? And then comes the harder question, what does typically even mean, if the ensemble is generated by eternal inflation and regulated by a contentious measure? The cosmological constant is the central example, because it looks absurdly small and strangely timed. Naive quantum field theory suggests vacuum energy should be enormous, because every field contributes 0-point fluctuations. If one cuts off the calculation at high energies, the predicted value is many orders of magnitude larger than what we see. Observations show dark energy is tiny but non-zero, and it dominates only recently in cosmic history. The mismatch is so severe that it has been called the worst theoretical prediction in physics, not because the math is sloppy, but because the expectation seems natural and the answer seems alien. That recently is not just a narrative flourish, it is a measurable coincidence. For billions of years, matter dominated the expansion, allowing gravity to build galaxies and clusters. Only after structure formed did dark energy begin to accelerate the expansion significantly. Why should the vacuum energy be small enough to wait, but large enough to matter now? The timing invites suspicion that we are missing a dynamical mechanism, yet it also invites the possibility that we are seeing selection at work. If the cosmological constant scans across the landscape, then most universes expand too fast for galaxies. The basic mechanism is simple in plain language. If space accelerates too early, matter cannot clump, and the raw material for stars never condenses. In a more technical description, accelerated expansion suppresses the growth of density perturbations, preventing them from becoming nonlinear. Without nonlinear collapse, there are no long-lived gravitational wells to host complex chemistry. The selection window is narrow because it is tied to the competition between expansion and gravitational instability. and that competition is sensitive to a small vacuum energy. In that case, selection effects become a proposed explanation, and the proposal has a specific structure. We observe a small cosmological constant because only such regions form long-lived structure, and only long-lived structure produces observers. The argument is statistical, not teleological, and it is meant to rescue predictability. It also shifts the meaning of explanation from derivation to conditional typicality. A constant becomes less like a uniquely determined output, and more like a draw from an underlying distribution, filtered by the requirement that someone is there to notice it. This is where a thought-provoking question belongs, because the chapter is about the edge between physics and inference. If a parameter is environmentally selected, does that make it less real as an explanation, or simply different in kind? In biology, selection is a rigorous mechanism, not an excuse, and it produces quantitative predictions. The challenge is whether cosmology can reach that level of discipline with only one observable universe. And if it cannot, should we treat anthropic reasoning as a temporary bridge or as a permanent feature of fundamental physics? Criticisms are equally important, because anthropic reasoning can become a loophole if it is used carelessly. If parameters can vary widely, almost any observed value can be declared selected, and the argument becomes unfalsifiable. The reasoning can be hard to test because it depends on unknown distributions across the multiverse. It can also discourage the search for dynamical mechanisms that would otherwise be pursued. The healthiest version of the debate treats anthropic reasoning as a last resort, not a first instinct, while admitting that the cosmological constant problem keeps pushing us toward uncomfortable options. There is also a methodological worry that is easy to miss in casual debate. Anthropic reasoning often requires a prior distribution over vacua, plus a model of how observers arise. Both ingredients are uncertain, and both can dominate the conclusion if chosen poorly. When the uncertainty is large, the argument can feel like it explains everything, and therefore explains nothing. The documentary should let that worry breathe, because it is not a rhetorical complaint, it is a technical warning about sensitivity to assumptions. The tension is not only philosophical, it is technical, and it has a name that working cosmologists treat with seriousness. Eternal inflation generically produces infinite volumes of space and infinitely many bubbles, because the inflating background expands faster than it decays. If there are infinitely many observers, then probabilities become ratios of infinities. To predict anything, we need a measure that regulates the infinities and defines what counts as typical. In other words, we need a consistent rule for counting outcomes in a space-time where more volume is produced without end. This is the measure problem, and it is a crisis for prediction rather than a side complaint. Different cutoff procedures give different answers for the same question, even when the underlying dynamics are identical. Some measures produce paradoxes like the youngness problem, where most observers live in extremely young universes because volume grows so quickly. Other measures produce runaway behaviors, where certain vacua dominate simply because they inflate a bit longer. The problem is sharpened by relativity itself, because different choices of time slicing can change which events are counted before a cutoff is applied. The visuals can turn stark here, an endless branching diagram of bubbles, multiplying faster than any count can track. Numbers appear, then turn into infinities, then dissolve into question marks. The narrator's tone should feel steady, because the issue is not emotional, it is structural. When everything happens infinitely many times, how often becomes ambiguous. And when how often is ambiguous, the usual bridge from theory to expectation begins to wobble. Boltzmann brains are not a joke, they're a consistency check with teeth. In a long-lived de Sitter-like space, rare thermal or quantum fluctuations can assemble self-aware observers, complete with false memories. The probability is fantastically small per unit volume and time, but eternal inflation provides fantastically large volume and time. If such observers dominate the measure, then typical observations become incoherent and untrustworthy. The thought experiment is brutal because it forces a theory to confront its own statistical predictions, even when those predictions are counterintuitive. A theory that predicts we are almost certainly delusions is a theory with a problem, even if the mathematics is elegant. The point is not that Boltzmann brains are likely in any everyday sense. The point is that the measure can make typical detach from reasonable, and that detachment signals a mismatch between the model and the rules of inference. The multiverse does not only multiply worlds, it destabilizes probability itself. It also raises a quiet question. If our observations are atypical in a model, should we reject the model or revise what we mean by typicality? In ordinary physics, probability is tied to repeatable experiments and well-defined ensembles, even when the experiments are hard. We can imagine rerunning a particle collision, or sampling many atoms, or preparing many identical systems. In eternal inflation, the ensemble is the universe, and it is infinite. Prediction becomes sensitive to how we count, and counting becomes part of the theory. That is an inversion of the usual scientific posture, because we normally treat counting as bookkeeping, not as a dynamical ingredient. That is a strange place for physics to land, because physics usually tries to make counting irrelevant. We want predictions that do not depend on arbitrary choices, like where to place a cutoff or which time coordinate to prefer. Yet in an eternally inflating space-time, different time slicings can change the apparent abundance of events. The measure problem is partly a problem of gauge-like ambiguity, translated into statistics. The deeper worry is that even a correct underlying theory might fail to produce unique predictions, because the step from dynamics to probability is underdetermined. This is the disturbing implication the chapter builds toward, and it should feel like a slow tightening. If every allowed outcome happens somewhere, then explanation changes meaning, because uniqueness dissolves. We stop asking why a constant has one value, and start asking why we are in a region with that value. The shift is subtle, but it touches the foundations of scientific inference. It also changes what it means to be surprised, because surprise depends on a probability assignment, and the probability assignment depends on a measure. The camera can return to the cosmic microwave background at this moment, because it is our most ancient photograph. The CMB is a nearly uniform glow at 2.7 Kelvin, mottled by tiny temperature anisotropies. Those anisotropies are not just noise, they're a fossil record of primordial fluctuations. If a multiverse leaves any trace, it might be hidden in that faint texture. The image can linger on the grain of the map, hot and cold speckles only tens of microkelvin apart, because the entire argument is about extracting meaning from barely perceptible patterns. Now we widen the idea of outside again, beyond many universes toward more dimensions, because outside can also mean off the page. Higher dimensional models begin as attempts to unify forces and quantize gravity, and they have a long pedigree. Kaluza and Klein in the 1920s tried to unify gravity and electromagnetism by adding a fifth dimension. Modern versions appear in string theory and related frameworks, where extra dimensions are required for mathematical consistency. The historical arc matters because it shows that extra dimensions were not invented to rescue cosmology, but to repair the internal logic of unification. Extra dimensions can be compact and hidden, or large but warped, and those options change what experiments should see. Compact dimensions can be curled up at tiny scales, like circles so small that ordinary motion cannot resolve them. Warped dimensions can be large yet effectively hidden, because the geometry redshifts energies and localizes fields. In these pictures, our universe may be a brain embedded in a higher dimensional bulk. The visuals can make this concrete. Our visible cosmos is a luminous sheet, with gravity lines bending and fading into a dimmer surrounding volume. A brain is a lower dimensional surface where standard model fields can be confined, like vibrations trapped on a membrane. Gravity can propagate in the bulk, which changes its behavior at high energies or large distances. This is not just science fiction imagery, it is a concrete statement about field localization. If gravitons explore more dimensions than photons and electrons do, then gravity can leak, dilute, or strengthen in unfamiliar ways. That leakage is why tabletop tests of gravity and collider searches can, in principle, probe geometry that is otherwise invisible. Cosmology becomes a probe of geometry beyond our visible dimensions, because the early universe reached energies where extra-dimensional effects might matter. The Big Bang can be reinterpreted as a brain event, like a collision or a transition, rather than a singular creation. In some scenarios, two brains approach and collide, releasing energy into the brain we inhabit. In others, the brain moves through a bulk background, and its motion appears as expansion to brain-bound observers. The point is not that we have confirmed such pictures, but that they offer a different meaning of beginning, one rooted in higher dimensional dynamics. Brain-world scenarios can also mimic inflationary or bouncing behavior, which is why they belong in this chapter's sequence. The effective Friedman equations on the brain can be modified by bulk effects, adding terms that scale differently with energy density. At high energies, the expansion rate can change, altering the conditions for nucleosynthesis and perturbation growth. Energy exchange between brain and bulk can also change expansion history, though such exchange is tightly constrained. The models live or die on details because the early universe is a precision environment, and small deviations can cascade into large observational conflicts. These models are constrained by precision tests of gravity and by cosmological data, and the constraints are not gentle. Laboratory experiments test Newton's inverse square law down to sub-millimeter scales, looking for deviations that extra dimensions could cause. Astrophysical observations test gravity on large scales, where leakage into the bulk might alter dynamics. Cosmology tests the early universe, where even small changes can spoil the successful predictions of standard Big Bang nucleosynthesis. The documentary can underline the discipline here. Speculation is allowed, but it must pass through a narrowing gate of quantitative limits. Higher dimensions also connect to holography, which reframes what inside means by challenging our intuition about volume and information. The holographic principle suggests that gravitational physics in a volume can be encoded on a lower dimensional boundary, with roughly 1 bit per Planck area. In ADS-CFT, a higher dimensional bulk is dual to a lower dimensional quantum field theory without gravity. Space-time becomes an emergent description of deeper degrees of freedom. The historical context matters again, because holography grew out of black hole thermodynamics, where entropy scaling with area hinted that our usual notion of how much fits inside was wrong. This is a place where the visuals can become almost architectural. A glowing boundary surface, with the bulk interior appearing as a projection. Lines of entanglement can be drawn like threads, tightening into a geometry. The narrator can linger on the strangeness without overselling it, because the strangeness is already built into the math. If geometry can emerge from entanglement, then where is not fundamental in the way we assume, and if where is not fundamental, then outside may be a shift of description, not a new expanse to travel into. Holography is not automatically a multiverse theory, but it changes the ontology of what counts as fundamental. If our universe has a holographic description, then outside might be a different language, not a different place. The fundamental layer could be quantum information, entanglement structure, or boundary conditions that do not look like space at all. The chapter's theme returns because before may be a category error inside an emergent spacetime. The edge that isn't an edge may be the point where our familiar coordinates stop being the right vocabulary. That observation invites a careful question rather than a dramatic claim. When we ask what happened before the Big Bang, are we assuming that time is fundamental and continuous? If time is emergent, then before may not exist as a global coordinate, even if a local time emerges inside a region. The edge that isn't an edge may be an edge of description, not an edge of reality. The documentary should let that land quietly, because the most unsettling ideas often arrive without spectacle. These ideas are mathematically motivated, but their testability varies sharply, and the documentary should keep that tension visible. Extra dimensions can leave signatures in particle physics and gravity, but many are pushed to scales beyond current reach. Holographic dualities are powerful in specific settings, but our universe is not obviously anti-de sitter. The disciplined approach is to ask what could leave traces in data, even if the traces are subtle, and to admit, openly, that some traces might be indistinguishable from more conventional explanations. So we list potential observational hints, and we emphasize their fragility, because the universe does not hand out clean labels. Bubble collisions could leave circular or disc-like imprints in the CMB temperature or polarization, like bruises on an otherwise smooth surface. The idea is that our bubble might have collided with another during its early expansion. Such a collision could perturb the reheating surface, imprinting an azimuthally symmetric feature. In polarization, the pattern could show a distinctive alignment, but only if foreground dust and instrumental systematics are controlled with ruthless care. Searches have been performed using satellite maps and statistical templates, and no compelling signal has survived scrutiny. Some candidate features were reported and then weakened as data improved and foreground modelling sharpened. The absence constrained some collision rates and some inflationary histories, especially those predicting frequent energetic collisions. Yet the constraint is model-dependent, and the space of possibilities remains broad. The documentary can show the process, templates sliding across the sky, significance levels rising and falling, because the story is as much about method as it is about outcome. Spatial curvature is another handle, because inflation predicts near flatness, but not exact flatness in every scenario. If our bubble formed with slight open curvature, a small negative curvature could remain as a fossil of the nucleation geometry. Curvature affects the angular size of features in the CMB and the distance redshift relation in galaxy surveys. Current constraints from the CMB and large-scale structure push curvature very close to zero. That near zero result is itself a kind of clue, because it implies a substantial amount of inflation after nucleation, enough to iron out curvature to an extraordinary degree. That result does not kill the multiverse, but it narrows some bubble scenarios, and it sharpens the question of how much inflation occurred inside our bubble. Too little inflation leaves detectable curvature, while too much inflation erases it almost completely. The universe appears flatter than many early cosmologists dared to expect, which is both a triumph for inflation and a narrowing of certain multiverse signatures. The edge retreats again, not by disappearing, but by becoming harder to touch. The more inflation smooths our patch, the more it hides the very evidence that might reveal what lies beyond it. Primordial gravitational waves are a third handle, because they probe inflation's energy scale through tensor perturbations. A detection of tensor modes in the CMB's B-mode polarization would be a direct window into physics at extraordinary energies. It would support inflation broadly, but not eternal inflation specifically, because eternal behavior depends on the potential shape and quantum fluctuations. A strong tensor signal could also constrain landscape models by limiting potential shapes and field ranges. The key point is that tensors would not be a multiverse photograph, but they would be a calibration of the inflationary engine that makes multiverse scenarios plausible. The continued non-detection already disfavors some simple high-scale models, especially those predicting large tensor-to-scalar ratios. That does not mean inflation is false, and it does not mean the multiverse is false. It means the simplest versions are being squeezed, and the viable models are becoming more structured. In science, that is what progress often looks like. Not a single decisive blow, but a tightening corridor. The visuals can reflect that tightening, parameter plots narrowing, error bars shrinking, and once wide theoretical spaces becoming thin bands. Large-scale structure surveys add further constraints on primordial statistics, and they do it with a different kind of leverage. The distribution of galaxies traces the underlying matter fluctuations, which carry information about the early universe's initial conditions. Non-Gaussianity tests whether the early universe involved simple, weakly interacting fields or more complex dynamics. Many multiverse-adjacent models predict features, running, or non-Gaussian signatures, but the data remain consistent with near-Gaussian initial conditions. That near-Gaussianity is not just a number, it is a story about simplicity, about fluctuations that look like they were generated by a small set of fields in a relatively smooth phase. The allowed space is shrinking, but it is not closed, and that is the honest summary. Some models hide their signatures by design, because the relevant physics occurs at scales we cannot access. Others predict signals that are just below current sensitivity, waiting for better maps and better control of systematics. The multiverse remains an inference, not an observation, and the difference matters. The documentary should keep returning to that line, because it is the boundary between what we can responsibly claim and what we can only wonder about. We also acknowledge the hard limit that cannot be engineered away, because cosmology is not a laboratory with unlimited reruns. Cosmic variance limits what we can infer from the larger scales, where some bubble signatures might live because we only have one sky to observe. Foregrounds and systematics complicate polarization searches, where tensor and collision signals might hide behind dust and instrument noise. The multiverse may be constrained indirectly, but direct confirmation remains elusive. Even with perfect instruments, there are modes of the universe that are simply not available to us, because the universe gives us only one realization of its largest scale randomness. At this stage, the chapter ties back to earlier tension about inflation's beginning, because the origin question has not been solved, only displaced. Eternal inflation can generate many universes, but it still assumes an inflating background and a set of laws that govern it. The Borde Guth-Vlenken result still suggests past incompleteness for many inflating spacetimes, meaning they cannot be extended indefinitely into the past. Even a multiverse may have a boundary, or a regime where spacetime itself is not the right language. The chapter's mystery returns in a new register, less about what lies beyond our horizon, and more about what lies beneath the assumptions of the framework. This is an important narrative beat because it prevents the multiverse from becoming an escape hatch. If the multiverse is real, it may be vast, but it is not automatically eternal in the past. If it is not eternal, then the question of origin returns in a new form. What sets the initial condition for the inflating background, and what fixes the rules by which bubbles form? The regress is not a flaw in curiosity, it is the sign that we are pressing on the deepest layer of what a physical explanation can be. So the multiverse does not end the origin question, it relocates it, and relocation is not resolution. We can ask what selects the inflaton potential, what selects the landscape, and what selects the measure. Each selection can be treated as physics, or it can be treated as brute fact, depending on how deep the theory goes. The documentary's mystery deepens because the regress is not obviously stoppable, and if it is stoppable, we do not yet know what the stopping principle would look like: symmetry, consistency, or something more abstract than either. Now we sharpen the disturbing implication into a single narrative beat, and we let it land without melodrama. If there are infinitely many universes, then explanation becomes conditional and probabilistic, rather than unique and deductive. If probabilities depend on a measure we cannot uniquely justify, then prediction becomes unstable. If prediction becomes unstable, then the boundary between science and story becomes dangerously thin. That boundary is not a moral judgment, it is a methodological warning. Science earns its authority by connecting models to observations through rules that are public and reproducible. If the rules of counting are ambiguous, then two scientists can share the same equations and disagree on what is typical. The multiverse, in its most expansive form, forces us to confront that vulnerability. It asks whether our usual standards of explanation, uniqueness, inevitability, clean prediction, are features of nature, or features of the kinds of questions we evolved to ask. We do not resolve that tension here, because the resolution may not be cosmological, and it may not even be geometric. The multiverse and higher dimensions expand where the universe sits, but they still assume laws. They still assume a mathematical structure that generates vacua, bubbles, brains, and horizons. The next chapter confronts the deeper layer that remains even after outside is expanded. Transition. Multiverses and higher dimensions change the map, but they leave the rules untouched. Next, we ask what laws of physics are, and whether laws can exist without time. We have stretched the map with bounces, cycles, and multiverses, yet the same question survives in the silence between theories. Did anything exist before everything? Or did we smuggle time into the question, like a hidden assumption we never earned? Even the word before carries a direction, a sequence, and a clock face, and physics keeps asking whether those props belong in the deepest script. When we picture a beginning, we imagine a first frame of a film, a clock that starts, a line that extends backward. Yet physics keeps warning us that this picture may be parochial, shaped by brains that evolved inside a warm, expanding universe. The more carefully we define before, the more it depends on time already being there. So the question becomes sharper and stranger. Is time a basic ingredient or a derived feature that appears only under certain conditions? General relativity makes time part of the system it describes, not a background clock that ticks the same everywhere. The metric sets durations and distances, and matter tells that metric how to curve, an interlocking feedback that replaces absolute time with dynamical geometry. In Einstein's theory, time can slow, tilt, and end, because it is geometry rather than a universal metronome. What counts as a second is not handed down from outside. It is read off the structure of space-time itself. Visually, relativity invites a particular kind of image, a grid that is not drawn on paper, but woven into the world itself. Massive objects press the grid inward, and the lines of time lean and stretch near them, changing what simultaneous even means. Light cones narrow and tip, and the future becomes a direction carved by geometry rather than by intuition. A clock near a black hole is not merely running slow by convention. Its proper time is genuinely shorter along its path. The theory turns what we call time into something measured locally, along world lines, by physical clocks made of matter. This was not a casual philosophical move in 1915, and it arrived with historical force. Newton's absolute time had been a quiet foundation for centuries, and even early relativity had to fight for legitimacy. Einstein's insight was that gravity is not a force in space, but the curvature of space-time itself, so time cannot remain a detached stagehand. Once space-time becomes the actor, time becomes part of the script. The later confirmations, from gravitational redshift to GPS corrections, made the strange claim operational and unavoidable. Quantum mechanics treats time differently, as an external parameter that labels change rather than a variable to be solved for. The Schrödinger equation evolves a state with respect to a time that is not itself quantized, and in most practical calculations it is simply assumed. In the lab, we assume a clock exists, and we do not ask what the clock is made of, so long as it is stable enough to mark intervals. We treat time like a ruler on the edge of the experiment, not like a participant inside it. That assumption is so successful that it becomes invisible, and invisibility is dangerous in foundational physics. A quantum state can be a superposition of alternatives, and its evolution is unitary, smooth, and precisely timed. Yet the time in that equation is not an operator with uncertainty, and it is not something that fluctuates. It is a parameter we read off a classical device sitting outside the quantum description. In effect, the theory borrows a classical backdrop, even while it claims to replace classical certainty. This difference is easy to miss because it hides behind familiar words. Both theories say time, but they mean different things by that syllable. In general relativity, time is part of the dynamical field, and it can be warped by energy and momentum. In quantum theory, time is the label on the page, the independent variable that tells the wave function when to change. The same word masks two incompatible roles, one geometric and physical, the other external and bookkeeping. Put the two frameworks together and the mismatch becomes a wound in the foundations, not a minor translation problem. If spacetime is dynamical, there is no fixed time to evolve quantum states in the usual way. If quantum theory is universal, the clock should be part of the quantum system, subject to uncertainty and entanglement. This tension is called the problem of time, and it is not a semantic complaint. It is a demand for a single framework in which the clock is not smuggled in through the back door. The problem shows up the moment we try to quantize gravity in a way that respects general covariance. In relativity, the laws do not privilege a particular slicing of space-time into space and time, because different observers can cut the same space-time differently. Yet canonical quantization starts by choosing a foliation, a stack of spatial slices labelled by a time coordinate. The method works brilliantly for other fields, but gravity punishes the shortcut. The symmetry that makes relativity powerful becomes the symmetry that makes quantization slippery. In canonical quantum gravity, the conflict becomes explicit in the Wheeler-DeWitt equation, which functions more like a constraint than an evolution law. The equation often has no time variable at all, because the Hamiltonian that would generate time evolution becomes a condition that must vanish. The wave function of the universe appears frozen, even though the universe we inhabit changes from moment to moment. The disturbing hint is that time may be an approximation, not a primitive ingredient. The motion we experience may be encoded as correlations inside a state that, globally, does not tick. This frozen appearance is not a claim that nothing happens, and that distinction matters. It is a claim that the fundamental description may not be organized as a sequence the way our experience is organized. If the universe is described by a global quantum state, that state can encode correlations between subsystems without referencing an external clock. Change, in that view, is relational. One part of the state changes relative to another. The sensation of flow could be a feature of how subsystems track each other, not a property of the universe as a whole. There is a simple way to feel the tension without solving it. Imagine trying to write the quantum state of the entire universe, including every clock, every observer, and every device that measures time. If the clock is inside the system, what does the system evolve with respect to? The question loops back on itself, and that loop is the problem of time made concrete. It is like trying to define north using only a compass that needs north to calibrate itself. We can still ask where classical spacetime stops being reliable, and physics gives a sharp signpost with three linked scales. The Planck length is about 10 to 35 meters, where quantum fluctuations of geometry should become unavoidable. The Planck time is about 10⁻43 seconds, where the notion of earlier may lose operational meaning. the Planck energy is about 10⁻⁹ GeV, where known forces and gravity collide. These scales are not guesses. They are the units you get when you force nature's constants into a single, uncompromising combination. These numbers are not arbitrary, and they are not merely small for dramatic effect. They are built from the constants that define our best theories: the speed of light, Planck's constant, and Newton's gravitational constant. Combine them, and you get the scale where quantum effects and gravitational effects are equally strong. It is the point where our two languages are forced into the same sentence. At that point, even the idea of a sharply defined distance can blur, because measuring devices must themselves gravitate. At that frontier, we cannot simply rewind the cosmic film with today's equations, because the projector itself becomes uncertain. General relativity predicts singular behavior, which likely signals missing degrees of freedom rather than a literal point of infinite density. Quantum field theory assumes a space-time stage that may not exist at that scale, because fields are defined over a background geometry. The Planck regime is not a blank page, it is a warning that our language is breaking. When geometry fluctuates, the very notion of where the field lives becomes part of the problem. A singularity in relativity is often misunderstood as a physical object, like a dot you could point to. In practice, it is a sign that geodesics cannot be extended, that the theory's predictive power ends, curvature invariants blow up, and the equations stop being trustworthy. Historically, singularities were treated as pathologies, and then as features, and now again as clues that something deeper is missing. Penrose and Hawking's singularity theorem sharpen the issue by showing how generic collapse, or expansion, can drive space-time to an edge. Quantum field theory has its own warning signs, even when space-time is treated as fixed. Vacuum energy diverges unless we regulate it, and renormalization works because we can separate scales. But gravity couples to energy itself, including vacuum energy, so the bookkeeping becomes treacherous. At the Planck scale, the idea of a smooth manifold may be as approximate as the idea of a perfectly rigid solid. The continuum could be a useful limit, like a smooth shoreline seen from far above, while the microscopic structure remains unseen. This is where the documentary turns from events to conditions, from history to consistency. If time is emergent, the Big Bang may not be a first moment in time, the way a match strike is a first moment of flame. It may be a boundary of the domain where time is a useful coordinate, a limit of the chart rather than a point on the map. Asking what happened before could be like asking what is north of the North Pole. The question may fail not because reality refuses to answer, but because the grammar assumes the very thing under investigation. That analogy is not a dodge, and it is not meant to shut curiosity down. On a sphere, north is a direction defined locally, and it stops being meaningful at the pole because all directions south are equally valid. The question fails because the coordinate fails, not because reality is empty. In the same way, before may depend on a time coordinate that ceases to exist at the boundary. The edge is not necessarily a wall, it may be a place where the map changes its rules, yet the mathematics does not become empty when time becomes questionable, and that is crucial for keeping the discussion scientific. It still encodes structure, constraints, and allowed states, even if it does not narrate them as a sequence. The universe can be described by a wave function, and that wave function can be shaped by boundary conditions, much as a drumhead's vibrations are shaped by how its rim is held. The unsettling possibility is that the deepest layer is not a timeline but a rule. A rule can be silent and still be decisive, selecting what can exist without telling a story in words. A boundary condition is not a story, but it can generate stories. In ordinary physics, we often specify initial data and then evolve it forward. Here, the emphasis shifts. We specify what kinds of global configurations are permitted, and classical time emerges only in regimes where the permitted configurations look like evolving histories. The beginning becomes less like a spark and more like a mathematical selection. If that feels cold, remember that selection principles already guide physics, from least action to symmetry constraints, and they often feel abstract until they predict something measurable. One family of ideas replaces a sharp beginning with a smooth geometric condition, and it does so with a specific proposal. Hartley and Hawking propose a no-boundary state, where the universe is finite but has no edge, like the surface of the Earth without a boundary line. The beginning resembles a rounded cap, not a corner where equations explode. In that picture, the word before does not apply, because there is no earlier side of the cap. The proposal uses a path integral style sum over geometries, weighting them in a way meant to define a natural quantum state. To visualize it, imagine a camera gliding over a curved surface that looks like a sphere, but with one region that gradually opens into the familiar expanding universe. There is no seam where the surface starts, only a smooth change in character. The geometry closes off gently, and the would-be singularity is replaced by regular curvature. The start is not a point in time, but a place where the description changes form. On screen, the cap can feel like a soft dawn, geometry brightening into expansion without a violent flash. Historically, this proposal arrived in an era when cosmology was becoming quantitative, not just speculative. Inflationary theory was gaining traction, and quantum cosmology was trying to define what it even means to quantize the whole universe. Hartley and Hawking were not merely smoothing a picture for comfort. They were attempting to define a wave function with a clear prescription. The ambition was to replace arbitrary initial conditions with a principled choice. It was also a response to a growing sense that initial conditions might be a placeholder for deeper law. Vilenkin's tunneling proposal offers a related but distinct boundary story, and the difference matters in the details. The universe is said to tunnel into existence from a classically forbidden regime, borrowing language from quantum barrier penetration. The language sounds like a moment, yet the formalism is about selecting a quantum state, not describing an event inside time. The key move is that the beginning is not a time slice, it is a condition on the wave function. In this picture, creation is a weighting of possibilities, not a spark in an already running clock. Tunneling in ordinary quantum mechanics is not a particle deciding to break rules, it is the consequence of a wave function that does not vanish where classical energy would forbid motion. In cosmology, the barrier is not a wall in space, but a region in configuration space, where certain geometries are classically inaccessible. The proposal weights particular histories differently, and those weights can favour certain kinds of early expansion. What looks like a dramatic leap is, mathematically, a statement about which solutions are emphasised by the quantum measure. To make this accessible, we have to explain a technical trick without hiding its meaning, because the trick carries the conceptual punch. In ordinary spacetime, time has a different sign in the metric than space, which makes it Lorentzian and gives light cones their structure. In Euclidean approaches, time is rotated into an imaginary direction, and the sign difference disappears, turning oscillatory behaviour into something more like exponential damping. The equations can become smoother, and singular edges can soften into regular geometry. It is less like changing reality, and more like changing the coordinate language used to define a difficult integral. This rotation is often called a Wick rotation, and it is familiar in quantum field theory as a way to make integrals converge. In Lorentzian signature, amplitudes can oscillate wildly, and the path integral can be hard to define. In Euclidean signature, the same expressions can become better behaved, like a rough sea becoming a calmer surface. The mathematics becomes tractable, and tractability is not trivial when you are defining a universe. A calculation that diverges is not merely inconvenient, it can mean the question was posed in the wrong variables. Euclidean time is not the claim that time is literally imaginary in our experience, and it is not a mystical escape hatch. It is a way to compute probabilities and select states using better behaved mathematics, then translate back to the Lorentzian world we inhabit. The rotation can turn a violent beginning into a regular boundary condition, replacing an edge with a smooth closure. The narrative impact is that the beginning can be a change of signature, not a first tick. On screen, the shift can be shown as a hard-edged cone relaxing into a rounded dome, then reopening into an expanding spacetime. If this sounds abstract, consider what it changes in the visual language of cosmology. A singular Big Bang is often drawn as a sharp point, a corner where all lines converge. A no-boundary or Euclidean capped picture replaces the corner with a rounded geometry, where the lines curve smoothly and never meet in a tear. The universe still expands, but the origin is not a puncture in spacetime. The camera can linger on the difference, sharp cusp versus smooth cap, and let the viewer feel how much meaning rides on a shape. This does not solve everything, and the documentary should keep the uncertainty visible rather than polishing it away. We still have to explain how Lorentzian time emerges and why it points the way it does, because a smooth cap does not automatically give an arrow. We still have to connect a boundary condition to the thermodynamic arrow we live inside, where entropy increases and memories accumulate. The proposals are compelling because they are precise, not because they are complete. Precision is what makes them vulnerable to being wrong, and that vulnerability is a virtue. The arrow of time is not a mere psychological feeling, and it is not guaranteed by the fundamental equations. Most microscopic laws are time reversal symmetric, yet macroscopic life is not. Cosmology ties the arrow to special conditions in the early universe, including low gravitational entropy and the growth of structure. So any boundary proposal must do more than remove a singularity. It must also make sense of asymmetry. Why did the early universe begin in such an ordered state, especially in its gravitational degrees of freedom, when gravity tends to amplify clumping and complexity? Now the story widens again, but in a different direction than Chapter 5, and the widening is conceptual rather than geographical. Instead of adding more universes, we question whether space-time is fundamental at all, because the problem of time hints that our stage may be a derived object. Quantum gravity approaches increasingly suggest that geometry may be emergent from deeper degrees of freedom, as temperature emerges from molecular motion. If that is true, then the beginning of space-time is not a moment, it is an emergence. The first instant becomes a phase transition in description, where the right variables change. Emergence does not mean illusion, and it does not mean anything goes. It means that a higher level description becomes valid when many underlying degrees of freedom organize in a stable pattern. A fluid is real, even though it is made of molecules, and its waves are real, even though they're collective. Space-time in these approaches might be the fluid, smooth, useful, and approximate. If we zoom in far enough, the smoothness could dissolve into something more discrete, more informational, or simply more alien to our inherited intuitions. The holographic principle is the sharpest clue that our volume intuition can fail, and it arrives from black holes rather than from cosmology. Black hole entropy scales with area, not volume, implying a limit on information stored in a region. That scaling is not a detail, because entropy counts microstates, and microstates are what a theory is made of. Holography suggests the physics in a bulk can be encoded on a boundary, as if the world were written on its edges. The horizon becomes a ledger, and the universe begins to look less like a container and more like an accounting system. The historical path to this idea is itself a lesson in how physics advances. Bekenstein argued that black holes should have entropy proportional to their horizon area, and Hawking showed they radiate thermally, giving that entropy a temperature. The combination forced a radical conclusion. Black holes are thermodynamic objects, and their entropy is enormous. If entropy measures information, then the horizon is an information-bearing surface. The paradoxes that followed about what happens to information when a black hole evaporates kept the principle from being a curiosity and turned it into a pressure test for quantum gravity. This is not just a metaphor, it is realized in specific dualities like add-CFT, where the statement becomes mathematically sharp. A gravitational theory in a higher dimensional bulk can match a non-gravitational quantum theory on a lower dimensional boundary, with observables mapped across the correspondence. The mapping is exact in those settings, and it changes what we mean by space, because the bulk can be a derived description of boundary degrees of freedom. The inside becomes a way of organizing the edge. Even if our cosmos is not that space-time, the lesson remains. Geometry can be a translation, not a starting point. In visuals, holography invites a striking reversal. We watch a three-dimensional region filled with fields and motion. Then we watch that region flatten into a boundary surface covered in data. The boundary does not look like a place you could live, yet it can encode everything about the bulk in the dual description. The camera lingers on the edge, and the edge becomes strangely authoritative. The audience is left with a quiet question. If the boundary can do the bookkeeping, what exactly is the bulk? Our universe is not obviously anti-de sitter, so we do not overclaim direct application, and caution is part of the scientific tone. Still, the conceptual lesson is hard to unlearn once seen, because it is not tied to one geometry alone. Space can be emergent, and the emergence can be controlled by quantum entanglement, the uniquely quantum linkage between subsystems. Geometry can be a way of summarizing correlations, not a stage that exists first. If correlations change, the effective geometry could change with them, and distance becomes a statement about information flow. Entanglement becomes a builder of distance in these ideas, and the claim is both technical and intuitive. Highly entangled degrees of freedom behave as if they are close in the emergent geometry, because information and influence are shared densely. Weakly entangled degrees of freedom behave as if they are far apart, because their correlations are sparse. The fabric of space becomes a map of relationships inside a quantum state. In that map, adjacency is not about coordinates, it is about shared quantum structure. This is where quantum information enters as more than an analogy, because it provides calculable tools. Tensor networks provide toy models where connectivity arises from entanglement patterns, and where cutting the network relates to entanglement entropy. A network of tensors can reproduce features of gravitational geometry, including how areas relate to entanglement entropy in holographic settings. The point is not that the universe is literally a network diagram, but that geometry can be reconstructed from information structure. The surprising move is that shape becomes a summary of who is entangled with whom. Imagine the visual language of this idea. Nodes connected by threads, then the threads thicken where entanglement is strong. The network begins to look like a scaffold, and the scaffold begins to look like space. Distances become emergent lengths, defined by how many links separate two regions of the state. The viewer is invited to feel the reversal, where comes from how related. In a slow dissolve, the network's abstract lines can bloom into a continuous landscape, as if geometry were condensing out of pure connection. If space can emerge from entanglement, time may also be emergent from correlations, and that possibility brings us back to the original question with new sharpness. Some approaches treat time as arising from relational change between subsystems, where one subsystem acts as a clock variable for another. Others treat time as an approximate parameter valid only in semi-classical regimes, where space-time behaves classically enough to define trajectories. In a timeless fundamental description, dynamics can be encoded as consistency among correlations rather than as evolution in an external parameter. What we call later may be a stable ordering inside the correlations, not an absolute label written on the universe. This returns us to the problem of time with new force, because it reframes the Wheeler-DeWitt constraint as a clue rather than a failure. The Wheeler-DeWitt equation suggests the universe is described by a state that does not evolve in external time, because there is no external time to appeal to. What we call evolution could be an internal bookkeeping, where one part of the state serves as a clock for another. Time becomes a perspective inside the wave function, not a universal background. The unsettling part is that the flow may be something like a useful gauge choice, real in experience yet not fundamental in the equations. A relational clock is not as exotic as it first sounds, because we already live by relational time in practice. We do not see time directly, we see changes in clocks, atoms and oscillations, and we compare them. In quantum cosmology, the same logic is pushed to its limit because there is nothing outside the universe to compare against. The universe must carry its own reference frames within itself. The question becomes which degrees of freedom can play that role reliably, and how classical stability emerges from quantum uncertainty. In that framework, the beginning can be reinterpreted as a boundary condition on allowed correlations, rather than an initial instant. Instead of specifying an initial moment, we specify a consistent global state, including the correlations that will later look like a classical history. The universe is not launched, it is constrained, as if reality is the solution set to a deep equation. The disturbing implication is that the deepest explanation may be logical rather than historical. We are used to causes preceding effects, yet here the explanation can look more like a consistency requirement that simply holds. This is the climax of the documentary's central question, and it should land with quiet force rather than spectacle. If time is emergent, then asking what existed before everything may be ill-posed, not because the universe is evasive, but because the grammar of the question fails. There may be no before, because before requires a time parameter that does not exist fundamentally. Our intuition demands a prior scene, yet the theory offers a boundary of description. The boundary is not a curtain hiding a stage, it may be the edge of what stage even means. Still, the story does not collapse into emptiness, and that is what makes it unsettling rather than nihilistic. Even without fundamental time, there can be a prior structure in a different sense, a structure that does not sit earlier, but sits deeper. There can be a space of possible states, a rule for weighting them, and a condition that selects one. The universe can come from not nothing, from structure without chronology. The mind resists this because it wants a sequence. Yet physics sometimes answers with a constraint. This is where the word disturbing earns its place, because it challenges the hierarchy we instinctively trust. The deepest layer may not be matter, energy, or even space-time, because those are the things that change in time. It may be relationships, constraints, and informational patterns that do not require time to exist in the usual sense. The universe may be less like a story that starts, and more like a consistent solution that contains stories inside it. If so, then existence is not an event, but a property of belonging to the allowed set. That shift also reframes the old debate about nothing, which has always been haunted by ambiguous definitions. A vacuum in quantum field theory is already structured, with fluctuations, correlations, and a non-trivial ground state shaped by the fields and symmetries. Even empty space has measurable effects, from the Casimir force to vacuum polarization. A timeless foundation would be structured even more abstractly as a rule space of allowed quantum states. The uncomfortable question is whether nothing was ever a coherent physical category or only a linguistic temptation. So the question becomes why there are rules at all, not what happened first, and that is a different kind of mystery. It is not answered by pointing to an earlier cause, because earlier may not exist at the fundamental level. It is answered, if it can be answered, by understanding why certain mathematical structures are realized and others are not. The documentary does not claim to solve that, but it insists we see what the question has become. When the beginning becomes a boundary condition, explanation shifts from chronology to principle. We also have to confront a practical consequence for cosmology, because boundary conditions are not just metaphors. If the beginning is a boundary condition, then initial conditions become less like arbitrary inputs that we tune by hand. They become part of a selection principle, like regularity, minimal action, or consistency with a quantum measure. The universe's earliest state could be fixed by a requirement that the wave function be well-defined, normalizable, or smooth in a Euclidean regime. In that sense, the origin becomes a demand for mathematical coherence, and coherence becomes a physical criterion. Yet selection principles can hide ambiguity, and the documentary should not pretend otherwise, because seriousness requires admitting the open seams. Different boundary proposals can reproduce similar semi-classical universes, especially once inflation is allowed to wash away many details. Different quantum gravity programs can agree on low-energy physics while disagreeing on deep ontology, because they converge where we have data. The danger is that timelessness becomes an escape from falsification, unless it yields specific signatures. If the proposals cannot be distinguished even in principle, then they risk becoming aesthetics rather than science. So we ask what could ever be tested, and we keep the standards clear, because mystery without discipline becomes mythology. A no-boundary state can imply specific predictions for primordial perturbations in some models, including how likely certain inflationary histories are. Tunneling proposals can weight inflationary histories differently, changing expected curvature or tensor amplitudes, and shifting what typical universes look like under the measure. Holographic ideas can constrain entropy bounds and the allowed spectrum of fluctuations because information limits become physical limits. The challenge is that these predictions often depend on how we define the measure, and measures are where cosmology becomes both technical and treacherous. Even then, the signals may be subtle and entangled with astrophysical uncertainty, and subtlety is the price of probing the earliest accessible times. Cosmic variance limits what we can learn from the larger scales, where boundary effects might show up most clearly. Foregrounds and systematics complicate polarization, where tensors might carry clues about high-energy physics. The universe may be giving us a single dataset to infer a timeless foundation, and that dataset is noisy in ways we cannot average away. We can improve instruments, but we cannot build a second sky for comparison. Still, the scientific posture is not despair, it is discipline, and the discipline has a recognizable shape. We look for robust consequences that survive changes in model details, and we distrust predictions that depend on fragile assumptions. We compare predictions for the scalar spectral index, running, non-Gaussianity, and tensor modes, because these encode the statistics of primordial fluctuations. We ask whether a boundary condition selects inflation, suppresses it, or replaces it with another early phase. We also ask whether it predicts distinctive anomalies, like unusual correlations on the largest angular scales, while remaining consistent with everything else we already know. We also look beyond the CMB, because the sky is not the only archive, and cosmology has become a multi-messenger science. Large-scale structure surveys test primordial statistics through galaxy clustering, lensing, and bias, translating early universe fluctuations into late-time patterns. Gravitational wave observatories probe backgrounds that could encode early universe dynamics, including signals from inflation-like mechanisms or phase transitions. Black hole thermodynamics and quantum information experiments test the principles that motivate holography because they probe how information and gravity coexist. Each line of evidence is partial, yet together they can corner a theory by forcing it to be consistent across domains. As the visuals shift from equations to data, the tone should shift as well, from speculative to forensic. We watch maps of the cosmic microwave background, mottled with tiny temperature variations, each one a fossil of an early fluctuation. We watch polarization patterns traced like faint brushstrokes across the sky, and we remember how hard they are to measure. We watch galaxy surveys build a three-dimensional web, and we ask what that web remembers about a boundary we cannot see. The camera can glide along filaments of galaxies like luminous threads, then pull back until the web resembles a statistical fingerprint. Now the chapter tightens its final turn, returning to the human question without surrendering to it, because the human question is the hook and the hazard. We ask what existed before everything because we experience time as a stream, and streams have upstream sources. If time is emergent, that stream is a local feature of a deeper state, like a current in a larger ocean. Our question may be a category error, yet it points toward the right mystery. The error is not stupidity. It is the cost of thinking with tools forged inside time. The right mystery is not a hidden moment before the beginning, waiting behind a curtain of equations. The right mystery is why reality has a structure that can generate time, space, and lawful change, and why that structure is stable enough to host observers. If the beginning is a boundary condition, then the universe is not explained by an earlier event, because earlier is part of what needs explaining. It is explained, if at all, by the kind of consistency that can exist without time, and the most unsettling observation is that consistency can feel less like a story and more like a fact that simply holds. Transition. After confronting a timeless foundation, we return to the sky and to evidence, because science earns its mysteries by testing them. We ask what observations could ever distinguish emergence from mere metaphor, and boundary conditions from storytelling. We ask what patterns in the sky would look unnatural under one proposal and natural under another, and we admit how hard that is. The camera leaves the chalkboard and returns to the night, where the oldest light still arrives, pixel by pixel, carrying whatever the beginning allowed. We end with a controlled unease that sets up the final chapter, because the documentary's promise is honesty rather than closure. The universe may not have come from nothing in the way we imagine, because nothing is rarely empty in physics. The deepest candidate for what existed is a hidden structure, perhaps timeless, perhaps informational, perhaps encoded on a boundary. The final question becomes why there are rules, and why this rule set allows a world like ours. We end where cosmology always ends, with data that survived the first light and still drifts through space. If there was a before, it must leak into patterns we can measure. Faint correlations, subtle twists, and statistical scars that refuse to wash out. Primordial gravitational waves matter because they would imprint a curling B-mode polarization pattern in the CMB. Those swirls are not just pretty geometry. They are a fossil record of space-time itself being shaken. A clean detection would set inflation's energy scale and narrow the inflatant's field range, turning a vague epoch into a calibrated physical process. It would also separate primordial B-modes from later imposters, like gravitational lensing and polarized dust, which can mimic the signal unless carefully modeled. Non-detections still bite because upper limits translate into hard constraints on how violent inflation could have been. Each null result pushes simple high-scale models into corners, favoring flatter potentials or mechanisms that generate structure without large tensor modes. In that sense, silence is still information, an absence that trims the space of plausible beginnings. Next comes 21 centimeter cosmology, mapping hydrogen through the cosmic dawn's long darkness, before galaxies fully lit the sky. The line comes from a hyperfine spin flip in neutral hydrogen, and it appears as an absorption or emission feature against the CMB. By watching that signal shift with redshift, we can reconstruct when the first stars heated the gas and when ionization carved bubbles into the intergalactic medium. It can test small-scale power, warm dark matter and exotic heating from new fields, because tiny changes in early structure alter the timing and depth of the trough. It could also reveal early black hole growth or unexpected radiation backgrounds, the kind that would rewrite our assumptions about the first luminous engines. Large-scale structure surveys turn galaxy clustering into a test of primordial statistics, using millions of galaxies as tracer particles. Local-type non-Gaussianity would show up most strongly on the larger scales, hinting at multiple fields or alternatives to slow-roll inflation. Equilateral or folded shapes would point to non-trivial interactions or non-standard initial states, as if the vacuum itself began in a more complicated quantum mood. CMB anomalies keep tempting before stories, from the cold spot to low multipoles and hemispherical asymmetry. On a full-sky map, they look like bruises on an otherwise uniform afterglow, features that invite narrative. Each could be new physics, or cosmic variants wearing a mask, because a single universe gives us only one draw from the cosmic lottery. Black holes offer another laboratory, where horizons force quantum theory to answer without the courtesy of direct experiments. Hawking radiation suggests that empty space near a horizon is not empty at all, and the information paradox asks whether nothing can truly erase a history. Even without reaching Planck energies, consistency conditions from black hole thermodynamics may constrain quantum gravity, narrowing what a viable theory of beginnings is allowed to say. Transition. The hardest limit is not technology, but horizons and undecidable questions. We may never access information from beyond our cosmic patch, so we demand falsifiable consequences inside it. Predictions that survive new data rather than new metaphors. 3 live possibilities remain: a prior phase, a broader structure, or emergent time. A bounce or cycle makes the before a physical predecessor, with traces that must seep into spectra and correlations. A multiverse or landscape makes the before a larger setting, where our patch is one outcome among many, and selection effects become part of the story. Emergent time makes the before a category error, because earlier only becomes meaningful after certain degrees of freedom lock into a clock. None makes nothing simple, and each makes before a different word. The disturbing discovery is structure in the void, and our beginning intuitions failing under measurement, because the universe keeps answering with patterns, not origins. We began at a crime scene, not a mythic flash, reading the universe's surviving evidence in Redshift's primordial elements and the CMB's faint acoustic ripples. The deeper we pushed, the less nothing behaved like absence, and the more it behaved like structure. Quantum fields with ground states, horizons with temperatures, and boundary conditions that act like invisible architecture. Inflation could smooth the early cosmos and seed galaxies, yet it also opened darker doors, from eternal self-reproduction and a multiverse with a measure problem, to bounces and cycles that replace a singular cliff with a transition. And when we finally asked what sits at the past edge of every model, we ran into the most disturbing possibility of all, that time itself may be emergent, and the beginning may be a boundary condition rather than a first moment. Our best tests are still indirect and fragile, hunting for scars in polarization swirls, in 21-centimeter hydrogen maps, in non-Gaussian patterns, and in the stubborn anomalies that might be new physics, or merely cosmic variants. So the story has not narrowed to one tidy origin, it has widened into 3 competing befores, plus a 4th option that says the word before may not apply. In every chapter, the same tension returned. The singularity as either a real beginning or a warning light, and the vacuum as either the closest thing to something from nothing, or proof that nothingness never truly existed. Even the multiverse, if it's real, doesn't end the search, because it trades one question for another: who chose the landscape, the measure, and the rules that make any universe calculable? What we have at the end is a map of our ignorance that is sharper than it used to be, and a set of predictions that could still surprise us, because the afterglow remembers more than we can currently read. So what did the universe explode out of? Another cosmos, a quantum field, a timeless structure, or a trap in how we imagined before? The most honest answer is that the hot Big Bang looks like a beginning in our equations, but the deeper beginning may be the appearance of time from hidden relationships, where before becomes a category error and origin becomes a question about rules. If the universe did not come from nothing, then the disturbing discovery is not that something was there first, but that there are constraints, laws, symmetries, and boundary conditions that can exist without a clock to tick. And maybe the oldest mystery is not what happened before the beginning, but why reality is the kind of thing that can have a beginning at all. Watch the next generation of sky surveys and CMB, gravitational wave and 21 centimeter experiments closely, because the faintest patterns may decide whether before was a phase, a multitude, or an illusion.